Take a simple song like Twinkle Twinkle Little Star or something, very simple children's song, and suddenly give
Steve, they can't really hear you. Maybe turn the water off a little, or speak louder.
Yeah, or give it expression. You know, we can make it expressive. Expressivity is possible. We can get this level of expression that's not possible with other instruments. It's very fluid and flowing. And so the idea here is that we're able to use this as an expressive tool. And water is very important. You know, the Ontario is home of Lake Superior, which is the world's largest freshwater lake. So, and the Great Lakes we have here hold 21% of the world's freshwater supply, 85% of North America's freshwater supply. So in some sense, Ontario is water capital of the world. It's, you know, water stewardship is really important. And so this idea of water-human-machine interaction is something born of the 1960s. Growing up, you know, we would play around with these different kinds of water interfaces and build things. So I've done a lot at the intersection of humans and technology. The wearable computer from my childhood was an exploration of attaching computer systems to the body. But then water is another element too, you know, water and electricity. I was always afraid to swim because I had all this equipment on my body and water and electricity don't mix and everything. So I never really learned to swim in my childhood because I had all this cyborg technology on me. And so that was always the frontier. And I had this dual world of cyborg technology and water. And so what we sort of had this water cyborg idea that water is a medium of expression and interaction. So we put all kinds of sensing in here to control things. So the hydrolophone, an H2 organ, and all these different kinds of instruments were instruments of sensing and meta-sensing. So these are some early hydrolophones. There's Dr. Eugene Draw on violin here, and these are some early hydrolophones here. The original ones, you had to be underwater to hear them. The audience members and the player had to be underwater, but then we developed gradually a system whereby they could be heard above the water. And so each of these water jets is separately played, and we can get very expressive sound. We'll do, yeah, let's do that D Dorian. So yeah, this is the hydraulophone, the underwater musical instrument. And so it was kind of a long journey into the exploration of water, humans, and technology. And it's a really important nexus, a really important intersection. We have the cyborg technology. You know, we're all cyborgs now in many sense, but you know, the idea of humans and machines intertwining or intersecting. We have all these human-machine interfaces now that bring us these sort of superhuman capabilities. And so these are some of the early prototypes. When I was growing up in the 1960s, you know, we'd play around. I'd try and plot graphs and sound waves on the television screen, and then you know, my dad got me that cathode ray oscillograph there in my childhood, and it wasn't working properly, and the time base didn't work, and the dot only went up and down. So I kind of developed this. You know, I wanted to see it. I was impatient, so I put it on rollers like this so I could slide it back and forth on my workbench really quickly while I was looking at the screen. And then I was able to see. And what I discovered is I could see sound waves in air, in water, and in solid matter. And so I played around a little bit, you know, and we would often use radar to measure cars and boats and that sort of thing. So marine radar in the early days. My in our family, some of our relatives were in the Navy and on the East Coast, and so we'd often find ourselves touring ships and looking at radar and everything. And I started playing around with marine radar, and so I developed this interactive water-human-computer interface kind of thing that was called the sequential wave imprinting machine, SWIM. And what we do is we'd swim this hydrophone through the water and look at the response of it on a lock-in amplifier. A lock-in amplifier is this kind of instrument here, PAR124A, right here, is to this day the best amplifier ever made in human history, even like at Stanford University, Los Alamos Labs, MIT. They all use this amplifier when they're trying to measure the smallest, weakest signals. You know, and that's the gold standard. Nobody to this day has ever built an amplifier better than a PAR124A. And so that's kind of what I grew up with, 1961. And I was born in 1962. So, you know, it's from my childhood. This is what we use, and it's still to this day the best amplifier. And this is what we did, is we'd put a hydrophone on there and swim it through the water and put it on the oscilloscope with a broken time base and move the oscilloscope back and forth together with the hydrophone like this. And that would allow us to see the sound waves in the water. So it was perhaps the world's first water-human-computer interface from many, many years ago, called the sequential wave imprinting machine. And we did develop many other things. The hydraulophone is another interface. And the word interface is a double entendre. It means the boundary between different media like air and water, for example, the air-water interface. And it also means the computer interface, the border. So the border between humans and computers is the computer interface. The border between humans and water is the water interface. And there's also a border between water and technology, which is another interface. So you got these three interfaces. And so what we mean by water-human-computer interface is this interplay between these three borders and how they intersect. We can think of it as three circles on the Venn diagram. I use planet Earth is blue because it's mostly water, so I use that as the water circle. And then you've got the human circle. You know, you think of the Vitruvian person, you know, standing in the circle. That's kind of the iconic symbol of humanity, is a circle also. And then we've got the computer screen, which when in the 1960s, these were all these round, green, glowing screens with analog computers. Typically, back in the day, computers were analog, and they had round screens with the green glow that would vary. And you have this Pascal Fourier synthesizer here, or other things like that do Fourier synthesis on waves, and see these waveforms and compute stuff analog. And so when I think of water-human computer interface, I'm thinking of things like we built back in my childhood, which was these things that had this cathode ray screen, you know, the green glow of the tube. I'm going to say I've got one right here. This is your typical cathode ray tube. It's got an electron beam here. It shoots electrons at the screen, and there's a phosphor on the screen that glows. And we'd move that tube back and forth like this together with a hydrophone. So this tube would be on a vessel, like a little raft or something, and it would slide along in the water, and there'd be hydrophone in the water. And as we moved it along, we'd be exploring interactively and computing this interplay. So we had these really funny boundaries that didn't belong. So you got this tube running at, that one there runs at 2,600 volts. This one here only runs at 1,300 volts, but it's still a fairly high voltage. And so you got this high voltage thing next to the water. You got this interface between technology and the water, and then you got this other interface between the human and the technology, and between the water and the technology. So you get these three intersecting circles, and how do they interplay? And it's really interesting what that means. And then in 1998, we took this to University of Toronto, and in a collaboration with the McLuhan program, Marshall McLuhan, famous in the area of culture and technology. So the McLuhan program and Department of Electrical Engineering, we held a series of deconferences, which are kind of inverse conferences. And the idea of the deconferences was to explore the interplay between water, humans, and technology. And we did this. We created a whole bunch of different inventions, like an interactive shower system for mass decontamination, and all kinds of smart technologies using water and human computer interfaces. And so we held our 1999 was Decon 0, the first one, and then we had Decon 1 was in 2000, and then Deconference 2001 we turned into an art exhibit at Gallery TPW. Deconference 2002 was held right here in this building, and this building is called Decon sort of informally because I live here with my wife and 2 children upstairs, and downstairs is just my crazy lab, you know, where we can build stuff. And I've got milling machines and TIG welder and lathe and, you know, all that kind of stuff. You have to make things, and we would build stuff here and just have fun. We founded Interaxon out of here, the brain sensing company that makes a product called the Muse. My students and I and Ariel Garten founded that company right here in this space, and it kind of grew. We founded quite a few companies out of my home here, and so this has been a wearables center, and it's also the center kind of water, humans, and technology we call Decon. And so, Dr. Thank you very much for Dr. Eugene Draw for this beautiful musical fun.
Thanks, Steve. Thanks for having me. Always a pleasure.
And a big round of applause for Dr. Draw here. He's played with us at the Beaches Jazz Festival, and we've had this fun long history of hydraulophone music and improvisation. So I want to get started with Robert's talk. So Robert should be on. Is he on now?
I think so.
So let's get Robert on the line here at 10:30.
Trying to call Robert.
Okay.
So you're live in. Trying to call.
Okay, so you know what I'll do is I'll put this over here so it doesn't get okay. so wet.
We're live.
Okay.
You're
Good.
live in.
All right.
Trying to call.
Okay, so you know what I'll do let's just have some fun. Okay. So we're waiting for Thurman Rain. So
Trying to call.
yeah, let's just have some fun. You want to just so we're waiting for Thurman Rain. So yeah, let's have some fun. You want to just so we're waiting for well, you know what I could do is just want to make our ears a bit loud. We'll have some fun. You want to just so we're which is well, you know what I could do is just want to make our ears a bit loud. A lot of people don't like it. So it only has you know what I could do is just want to make our ears a bit loud. A lot of people don't like it. So it only has you know what I could do. So just if you listen to patterns and go. Actually, hang on a second. I'll start. I might just leave them over here. Okay, liquid nitrogen. BCs, B's next.
11.
Yeah, it's kind of like sort of dissonant, sort of
Yeah.
accelerating dissonance and consonance. And here, let's try.
Nice. He's not answering, so maybe you want to play till the break?
Yeah, so we'll
We
go
can talk.
till, how long do we got?
10:41.
Yeah. Okay, cool.
Oh, then it's just not there.
Also, Leaf Opperman is ready to present. So
Oh,
we could do that
actually, why
now.
don't we just have them present now? Yeah, that's a great idea.
Maybe turn that off and then we'll switch the audio.
Yeah, that's a good idea. We don't have to really stick to the script.
Yep.
So, let's say, okay, Leaf Opperman. Let's have him. Where's my? So, it's Leaf Opperman. Leaf, if you're ready to present, Leaf Opperman. Can I hear him?
Yeah, we're just gonna do.
Hello, can you hear me? Let me turn this one down. Turn this one down. Can you hear me? Leaf, can you hear me?
I don't.
Leaf, your microphone doesn't work. I guess Leaf's microphone doesn't work. Is it all right? I'll just turn it down. Okay, hang on a second.
Hey, can you hear Leaf on the Jitsi?
Hello, Leaf. Can you hear us?
Okay, go ahead.
Hello. Yeah, this is working, right?
Yeah, maybe just call the break.
Yeah, okay, let's just take a short break, and then we'll reconvene in about 10 minutes. Hello. So please welcome Leif Opperman. Leif will be talking about some of his work related to this kind of human water human computer interaction. Okay. Go ahead. You turn this one.
Just turn it very, have it very low.
Hello, Bob. Can you hear me?
No, now we can't.
Can you hear me? No. I can't hear him, and he can't hear me. Peter turned off to safe bandwidth. I can't hear him, and he can't hear me. Is anything here working?
Not sure.
Good.
Okay, we're streaming.
Good morning. How is everybody today? Hope all is well. My name is Bob Thurmond. I am from Angel Eye Technologies. We are an advanced vision system, an advanced vision system that does drowning detection technology worldwide. Been asked here today to kind of come with an overview about the state of technology in drowning detection and have a few basic insights.
Can you hear me? Leaf, can you hear me?
Did you just call my name? I thought Bob was speaking.
Technology. Let's see. I am going to, if we're at that point in time, let me share who I am and what I do. Let's do that. Let's go with this. And I will do this as a slideshow. All right. Is everyone on my page right now? Are we all aligned here? Do we have any other technology issues? Okay. So again, I'm Bob Thurman. I'm with Angel Light Technologies. I have been in aquatic safety and rescue for 20 plus years, and I'm based out of.
Can you hear us?
Sorry, can we continue? Continue. Okay. So again, aquatic rescue for 20 plus years. And one of the most recent enterprises that I've joined is Angel Light Technologies, which as an advanced vision system started in California with an LA County pool. And the reason it was done so is because there were several incidents in and around California that put a lot of pressure on the county to invest time in the exploration and data collection for drowning detection systems. So one of the challenges was that we, everybody that went through some kind of lifeguard training or had worked in, on, or around a pool deck or a lake or a beach, everyone pretty much knew that the deficits that the reasons lifeguard fail, right? They're not new. In fact, some of the information about conditions that made lifeguards ineffective, if you will, over time were known for 40 years. But the reality is that lifeguarding today. Is there latency there? Is that another latency?
Yeah, okay, let's just take a short break and then we'll reconvene in about 10 minutes.
Okay, that's definitely latency because I've heard that phrase a couple of times. So I'm going to continue. What our challenge is today is that we've got aquatic facilities that are much larger and more dynamic in terms of the features and activities that are going on in aquatics.
So please welcome Leif Opperman. And Leif will be talking about some of his work related to this kind of human water human computer interaction. Okay.
Okay. Okay. How's that doing now? All right, all right. So I am going to get back to my windows here. I apologize. I'm not. I'm the live stream is a little bit different for me. So okay. So what we were talking about is the sort of dynamism of aquatic facilities today, because we have new features and we have a lot of activities that require an additional effort with lifeguard and safety staff and personnel at water parks, at HOAs, even at small pools. So we are trying to sort of look way forward in the expectation that technology in our pools meets the technology that we understand and have come to expect in our in our businesses, in our homes. I always hate to say it, but my home is right at present time is way smarter than our pools, and that is sort of an insufferable type of position to be in when we know that we've got technology that can provide advanced detection, warnings about pool entry, and can record data day over day that provides a level of safety that is heretofore been unfeasible in our pools, but it should be, because it's not that particularly expensive. So I'm trying to share the screen here. Let me see if I can get on this, and I'll get back to this. No, that's not working super well. Unshare. Stop sharing. Okay, I need my tech gurus with me right now. Apologize. Here we go. Okay. It looks like I can do that. Can anyone see my screen yet? Let's go with this now. All right. Okay. So again, the sort of dynamic nature of these pools really illustrates, what we're looking at. We've got splashdowns, we've got objects in the water, climbing walls, etc. And this poses a particularly stark challenge on lifeguards themselves to do their jobs, which is why essentially most advanced vision systems are focused on a pool in a way that allows them to capture not only one body of water, but multiple bodies of water, and do so in a way that doesn't require additional lifeguards or staff. Apologize. So what are we looking at here? I'm looking at all of the new types of challenges that present itself to aquatics facilities, and I focus on North America, but really drowning is at the top of the food chain. But there are also a number of other challenges that present themselves to aquatic facilities, including first aid, theft, violence, vandalism, all kinds of stuff that happens on a pool deck, and what's now largely being characterized as antisocial behavior. These are all issues that aquatic facilities face, and they need to address in a way that is consistent across multiple pools and facilities. It's very difficult to say that you're doing the job that you've been set out to do in terms of safety and aquatics if you're not doing the same thing in a consistent way over multiple pools. So one of the things that I've talked about with Steve and a number of other people is this idea that we have essentially what's this expansive, safe, holistic program for adopting technology, and to look at that in a broad spectrum. So, what we're looking at here is we're looking at accident prevention, we're looking at crime prevention, and we're looking at education, and all of that from our company's perspective is to address gathering data that proves the efficiency and the quality of a technology system that operates in the water and on deck, right? Because we do want to capture ingress and egress from from a facility, but we also want activity that happens in the water. And I was surprised to learn that, in fact, a lot of antisocial behavior happens on deck prior to entering the water. So it's not just a drowning detection system. It's a much more holistic look at about aquatic safety over the perimeter of a facility, even extending so far out as possibly even a parking lot, right? Because we do get information from that, people entering and exiting a building. Are there any questions before I talk about this slide? Okay. So part of this is also, and I've set up this slide because what we realize is that in most pools, we have 3 levels of safety that is being encouraged in North America, right? Fences, covers, pool, or door alarms. And that's what I call sort of the primary level of safety features that are available today, right? They're passive systems. They don't evaluate. They don't provide advanced warning. They're prior to anyone entering the water. In an active system, in an active pool at any facility, go back. In an active pool, what we're looking at is a number of different elements that have to be considered, right? So we're looking at water quality, lifeguard training. We're looking about checking in and out pool equipment and messaging in between staff, either via phone or something like that, and lighting or strobes or any of those type of features that help people maintain and effectively negotiate safety in the pool. On the back end of this, which I think a lot of AI technology is pushing forward, is this idea that we can actually identify potential drowning or submersion threats in a pool, as well as capturing data that looks at antisocial behavior or social distancing or grouping in a way that facilities are supposed to be mindful of today. Really, what we're looking at as a result of COVID is also these the sort of the impact of social grouping that needs to be considered, and also the management of populations in our aquatic facilities. And at the end of the day, one of the things that I wanted to convey today is that AI technology in and of itself is not a replacement for quality lifeguard or safety staff. Really, what it does is it enables facilities to grow, maintain, and to promote the health and quality of life through swimming activities and all the things that we do in pools, and do it without additional facility staff and I think additional expense, in a way that I think is efficient and consistent with what we do at home and in our businesses. That's what I got. Steve, any questions from you or from the entire group?
Thanks for the presentation, Bob.
Yep.
Seems like I managed to solve my audio problem during your presentation. If you can hear me, it was definitely on my side. So great.
Oh, yeah. Yep.
Oh, great. Yeah, I'm so happy that you can hear me. Seems to have been an issue on my side. So I just go ahead. I'll go on screen share and give you my 20 minutes presentation, if that's all right. Cool. Okay. So you should be able to see that. Is that okay? Okay, thanks. Finally. Yeah, thanks for inviting me and being able to speak about projects we did at the institute that I work at, which is the Fraunhofer Institute for Applied Information Technology in St. Augustine near Bonn in Germany. I'm Leif Oppermann. I'm the group head of the mixed and augmented reality team in there. And we had a series of projects that I want to talk about most dominantly about the ARIF project, which was the bigger follow-up project, but there was also a seminal project that I briefly want to touch. So yeah, this work has been previously presented at the WaterHCI conference in 2016 in Florence when we were all still traveling. Got fond memories of the project and of the conference. And so here we go. Click on a link. I would like to start with a quick video so you get an impression, and I hope it streams well. My internet should be fast enough, but well, we had lots of problems, so let's see how it goes. Der Unterwasserwelt wird die Technik noch nicht so sehr eingesetzt. Es gibt erste Ansätze.
What the fuck?
Haben gerade alle Aufgaben gelöst und Signatur ist verabschiedet. Okay, so much for the video. I hope that came across well. So, of course, there's related work. There's a few pictures here. For us, it started with architectural visualization and stage planning. You can see an early prototype here on the top left. On the middle right, we've got a screenshot from a pervasive gaming project that I was working on as a PhD student. I did my PhD at the Mixed Reality Lab in Nottingham. I think I didn't mention that. So we were in pervasive gaming and things like that. In this domain that we are talking about, the related work that was relevant from our perspective was, for example, the 1993 wet PC, which was the first underwater PC that we found without tracking, without augmented reality, just an underwater PC. Almost 30 years ago now. Then we had the virtual Oceanarium in Lisbon in Portugal 20 years ago, which was a very large simulated underwater world, well, that you can explore virtually. And a couple of other systems like the Sea Slate and the Triton, which was quite prominent back then, and I think is still around. But they had no mobility support and they had no AR. So they were basically monitors on swimming pool walls. And so from there, my colleague Lisa and some other colleagues started working on the underwater AR system, which was mobile and included tracking. More related work first. Tracking objects in a pool is a repeatedly found task. So you have Simon Shelley with cleaning robots and other people with sonar and optical tracking, just for example. Then for the human-computer interaction, you got Lisa, that's Bloom et al. With the underwater AR game. You've got Pell and Müller from Australia with their artistic installation. I think Floyd is giving a talk later today, I saw from the program. Then you got Van Lucas to improve ROV navigation, and you've got Rafi introducing interaction categories across 6 degrees of water contact, which I think is quite interesting. So yeah, first prototype in a mask by FIT. Well, 13 years ago. Wow, time flies by. So the tangible aspects of the water changed the perception of the users. And we think it also, the prototype challenged the underlying assumption what AR could be or actually is. So it was a game with fish and treasures, and it was originally a student work, so very good final work of a student, and it got worldwide attention. So all the dive magazines in the world kind of featured it. It got Lisa a third prize at the SeaGraph 2009 student competition, and it was also featured on Canadian Discovery Channel. And I think if that hopefully works, it worked just before the conference. I'll give it a go here. Just a minute or so.
But it's a pity that we have nothing like that in Germany. So I thought, well, we could create a artificial.
I think that should do for the introduction. If you want a full video, you can check it on the YouTube channel. or just search for augmented reality underwater, or write me a mail. Right. So that was the prior work, and then we got the Arif project, which tried to put it into pool and into children's hands. So the first prototype was a bit clunky and fragile and also very expensive. So we tried to make it all a bit more low cost, and also while making safe, which relates to what Bob was talking about earlier. So yeah, augmented reality for water-based entertainment, education, and fun. That was the full title for our funny acronym. And we wanted to develop underwater AR experiences that you could deploy in water parks or swimming pools. It's a project from 2010, just December really, so 21 years ago, and running for 3 years. Led by us back then with participants, SME corporations in Germany and in Korea, and also subcontract in Korea. So 2 partners on each side. We were funded by the Korea Institute for Advancement of Technology, or short the KIAD, and we were the first KIAD funded project with the European lead organization, which gave us some kind of press also back in the day. Yeah, our mission statement from when we started, we thought that water is really a fascinating medium, and we wanted to develop fascinating underwater AR experiences. And when we looked back at prior work in the field of augmented reality, which I've also been doing for 20 years now, or back then for 10 years, basically everything had been staged in the medium air. And so that was all new territory, terra incognita, if you wish. So we wanted to bring computer games and entertainment applications from the desktop or your mobile device to mobile underwater using AR technology, and we wanted to pioneer that. Just a brief overview of our system. So as you've seen in the video, it's basically a tablet that was first a Galaxy Tab and then a Nexus 10 built into a waterproof case. We'll have pictures of that in a bit. And other than that, that was, of course, the standard Android operating system with the Unity 3D engine on that, and with tracking, and also, of course, content. So just a quick look at the engineering bits. So in year 1, that's the top picture on the right, we had a metal case with 26 bolts, which was very robust. We had touch improvements because, well, it was watertight, so you couldn't reach the touch screen, but the project partner, Umtech, filed for a patent after they found a solution to make the touch possible on this. And it was a single-player game. It worked, and we had to rework it in year 2, so we could go further. First improvement was to make the case a lot more lightweight. And that was reached with the introduction of a lot more plastic, which also finally gave a better Wi-Fi reception. And it was less than half the weight than in year 1. It probably still cracked the floor tile if you dropped it to the floor, but anyway, that was waterproof. Then in year 3, we refined the locking mechanism to make it easier to use, like a suitcase really. And yeah, we changed dimensions for the final hardware. In the first 2 years, it was the Galaxy Tab, and then for the final year, it was the Nexus. And we produced multiple of these units for our user testing, and we also made a prototype for wireless charging because that was deemed important by the water park experts that we talked to. Just a quick overview of what the experience would look like. You've seen it in the video already, but there's basically several kids in a pool at different underwater locations marked by metal plates. They would have little islands where they could interact while hovering or swimming above that island. And you would basically go on little mini quests that you would receive from the out of the water base station, and you would also have to take your results back to there. Yeah. As I already said, you move around, you explore the virtual underwater scenery, and you score at the base station. The background for this kind of designs was manifold, and not the least to Wi-Fi not spreading really well underwater. So we had to find a seamful way of playing with the Wi-Fi signal reception, really. Yeah, just a quick overview of the assets. So you've got the envisioned setup at the top, and in the middle you see the actual setup. Actually quite a nice shot. I was really pleased when we had that it worked out like that. The base station is just a low-cost waterproofed Nexus 10 tablet and a big marker. And then we've got 3 alu debond markers also that we sunk in the water. They were usually like a meter wide. And on the top right, on the bottom right, you see an example island. Yeah, for example, there's a little lobster over here. Yeah, more screenshots. I'll just skip those. More screenshots. So yeah, we wanted to evaluate that. So we wanted to find out if it was actually fun, and also if it would allow players to safely finish the game with a sense of satisfaction. It's more researchy way of saying it was okay and fun. And we wanted to find potential problems and challenges that we would have to address in future versions, or maybe others could address in future versions. And so what we did was a user-centered evaluation. We tested the game in a realistic environment, i.e. in a pool with kids, and we collected feedback for the game under as real conditions as we could, and children were of 7 to 12 years old. We used a mixed method approach using qualitative and quantitative evidence, which required quite some manpower, up to 5 researchers at the time. We also logged some events on the device itself, and I think there's a slide on it in a bit. We basically had a 1-hour time slot for 3 children, so we would welcome them, introduce them to everything. The parents would be around, of course. We would play the game, interview them, and they would get a little present at the end. Chronology was we first did a pilot evaluation in Darmstadt, Germany with 3 children. Then we would campaign to organize more players. Of course, we found that it's easier to do a campaign that people want to participate in than to ask people if they can send their kids over, which is usually not very well received. And we got a lot of feedback from that campaign, and many people wanted to participate with their children. And we got 36 players during that week-long campaign. Yeah, pictures from the test players at the pilot in Darmstadt. And so we tested the overall procedure of everything, including our evaluation methodology, and we wanted to establish a routine in the team. And we only had very minor refinements to do after the pilot test, which was one of the tasks was too complicated. There's a little game where you could clean the underwater world from some trash, and that was made a little bit easier. And we also just put the marker distance right. Then we went to Siegburg swimming pool, and yeah, I already talked about the details of the demographics. The pool area was about 8 by 8 meters and about 1 meter in depth. And so, yeah, find out if they played it well, if it was fun, and if it was fit for the market. So that was what we tried to find out. Yeah, that's what I mentioned as this slide about the mixed method approach. So we got the device logging, we've got video cameras over water and underwater. You can see my colleague Andy on the lower left. We got observers taking notes by hand, and we got questionnaires, little mini interviews that we did with the kids. Not very long, but just to get some evidence. So results, yeah. It was perceived as very novel, not a big surprise, but children had not seen anything like this before. We thought maybe in the games they would find something similar, but they haven't. Tracking worked. We did some basic tracking tests with custom-made tracking. Our group did custom tracking code in the past, and we also know how to use OpenCV, so we try to find ways of improving stuff underwater, but even in the project, like in 2011 or 2012, we already opted to go with the standard library, which was Euphoria back in the day, and we had no real issues with that. So we could just say that even 10 years ago, it was okay to just take a standard tracking library underwater and you would have no real issues. We found that you would want to keep the challenges simple. So children could have some fun and wouldn't be too confused, and also wouldn't be frustrated. So, for example, the cleaning trash was still a bit too complicated for some children, which caused frustration. And you don't want that if you just pay for something, probably. So, and you want to be very obvious. If something is not clear, it will cause confusion again. Also on the interface level, so we used touch input only for text entry, and then if you wanted to point at something, you would aim it. So it was a little crosshair in the middle of the display. Still, children try to touch on things because, of course, that's what they know. That's what you do with these tablets and smartphones. So yeah, make very obvious how you want to have the interaction. Marker distance for us worked fine with about 62 centimeter diameter on the short side for the marker size. Yeah, and it's related to the water depth. So if our water was a meter deep, you would have this kind of diameter. If it was deeper, it would be bigger, obviously. Smaller kids, of course, play in shallower water. You have to provide for that. If your markers are too big, maybe it's not so fun because they don't have the overview. Maybe it doesn't even work. So maybe make some smaller markers. We found that water current is an issue in the pool. It's actually not surprising, but sometimes you rediscover things that you could have known before. So of course there's fountains and vents, and they provide a flow of water. Not a big issue for a grown-up like us, but small children might, just flow away, and we've seen that. So they were a bit frustrated by that. And you might not be able to turn it off because it's not just you in the pool, and it might just be necessary for some other area very nearby. So you have to keep that in mind. Yeah, we logged data and a JSON file. So the start and the end of the mission, and every task that you completed or mastered, and on which island you were looking at. And then we turned that into graphics that are now coming up just very quickly. So here you see an example session of 3 kids, Paul 1, Paul 2, and Keenan. And you could see on which markers they were. The light, the middle, and the dark blue are different markers that they had aimed. And then you could see how long they played for. So Paul 2 was the fastest. But that's not necessarily the goal of the game. I mean, if you have a good game, maybe you want to play it longer, just, and then for the different events, you could see it when they found different fishes and so forth. And having this graphic allowed us to really unpack what happened in the game for each of the kids as part of the evaluation. If you are interested in the details, you can always read up in our mobile HCI paper, Playing on a Reef. Just like the name of this talk. So yeah, speed is an issue. We can see that in this graphics, Paul 1 was a lot faster than Paul 2. Yeah, he lost some tracking and caught air once. And okay. As clarity, you can see from the graphics that Paul 1 was a bit confused by the second mission. Which was the cleaning mission where you had to push trash over the edge of the island, and he tried again and again and again. And so that's the long blue bit bar at the bottom of the top. And of course, breathing is an issue. If somebody has continuous tracking of 2 minutes, it's probably not because he held his breaths for so long. It's more like he had his head above the water. So that's an interaction you will see. It's not like people will always dive or flow in the water. Maybe they just stand and have the head above the water, stuff like that. Yeah. Test user Fabian really enjoyed the graphics. So he stated in the interview that he just explored the world and he stayed longer because he liked it, and that was good. Maybe you get frustrated with some things, but maybe you're also very persistent. So we have Marcus here, who only caught his first fish after 73 attempts. So that's dedication. He thought it could be improved though, but for him it was part of the game, and then he tried it so many times. That was amazing. Yeah, general feedback, as kind of was to be expected after everything worked out. I'm always very nervous when evaluation starts, but you soon get a feel if it works out or not. And we got overwhelmingly positive feedback. Children really like to catch fish. That was their favorite bit. Cleaning trash wasn't so well received. And the treasure box also wasn't so well received. It wasn't so much fun. But catching fish was really good. They like the Arif system. You can see that on the diagrams. And, you know, some of them would rent it. Well, 35 out of 36 would say they would rent it and ask their parents maybe to get some money. The difficulty was about right. Some things were too complicated. Some were too easy, but generally was okay. So some discussion about the waterproof case. Ours was still slightly too heavy after the third iteration, and maybe make it floating on the water surface was some thoughts we had. But generally it worked. Handling was okay, not all super fantastic, but okay. Kids liked it. That was good. The swimming pool director liked it, and also the TV report was quite positive. We learned that swimming pool installation needs to consider water taps and water fountains, as already mentioned, for future wishes, just from our evaluation. And again, more details on the paper. More virtual scenery, longer playtime, maybe even. I mean, we had 20 minutes, but they would have liked to play maybe half an hour or up to 90 minutes, someone said. You could have other themes and again, smaller, lighter case, recurring issue, I think especially from the smaller kids. Here's an anecdote from a father who spoke to me, watching his son playing well underwater, and he was usually afraid of being underwater, he said. But not so with the game. So the father was really happy that the son happily dove underwater and just didn't think about his anxiety while doing this. And so the father was clearly very pleased about that. And maybe the game had to mitigate the anxiety. I think it did. So maybe that could be an aspect that can be designed for in VR, AR, XR, whatever. Yeah, upshot. You can do underwater AR apps for sure. I mean, you can do underwater VR. We all seen that already. I mean, we had the feedback from discussions we did with expert interviews back in the day, and also when we tried to sell this, people want to put it on slides and put on masks and so forth, and throughput is an issue and stuff like that. But if you want to go underwater AR and not put it in a mask like we did in the first prototype, but make it safer for kids to use, standard tracking is good enough. The scenic content was very much appreciated. And this is also where most of the work is. I mean, one of our 4 partners, us included, one of the partners was a content expert. They were just doing 3D animations and games all day long. So that's what we're really good at. And I think that's where you see that the current companies that are selling VR experiences in this domain have their emphasis. They are really good at making content. The content, the engineering is not so difficult anymore. So yeah, waterproofness, that's of course an issue, but just having a waterproof device alone isn't enough, even if it's the latest iPhone. Back then it was the 7. We are farther now. We also tested it with the Sony Xperia Tablet Z, which was a brand new waterproof tablet back in the day. And we took it to pool. We spoke with Sony, and it worked. I mean, but you wouldn't have to touch because the water would be touching the capacitive screen all the time. So you would have random presses everywhere. So maybe the case wasn't such a bad idea, or maybe not using touch. Yeah. And if you put it in a case, you should allow for wireless charging, because otherwise it's so much of a nuisance. I mean, we lost our backup case in the first time slot of the first day, and because I didn't correctly close the case, I guess, and then one of the poor children had a tablet go bust a few minutes into the game, and well, was my problem, but we had a backup device. But the rest of the week we didn't have one, and we were extra careful to close the case properly with a lot of Vaseline and stuff. Yeah. So children and pool operators like this kind of stuff. Missions should be simple and clear, and physical movement in a pool is not a problem. So maybe this could be a model for spicing up old pools, just like the VR coaster now is a model for spicing up old roller coasters. So that's what we thought, yeah. Finally, after the project ended, we were also invited to Game City Festival in Nottingham, which was a big UK entertainment festival. It was a lot of fun to be there, really great. And yeah, it was also on television. We were invited. I almost met the Korean president back in the day because they set up a science fair and we were all invited. But German politicians took too much time, so she couldn't visit the science fair. But anyway, almost. So that's me and the Reef project and the underwater project. And if there's any questions, I'd be happy to take them. Thanks.
And also, I'm sure we're going to generate a lot of discussion because this whole field of research is just really expanding, and we'll probably have a lot of online discussions. So stay tuned to the WaterHCI page, and Leaf, if anybody thinks of questions or whatever, we'll post them there as well, and we'll have continued ongoing discussions. I want to introduce Kevin Mako because Kevin is probably the #1 product designer in terms of industrial design, in the startup space, and here in Toronto. And Toronto is kind of the epicenter of wearables and all that kind of stuff, and kind of water and wearables and everything. So, so Kevin, take it away. Oh.
Hey, Steve, I've got my mic's on, sound's on, everything's queued up. Yay, good, good. All right, we're in business. Hey, look, Steve, first and foremost, much appreciated for the invite to speak here today. It's always fun doing these talks. And look, Steve, you're an incredible innovator. And just for everyone out there, I've known Steve for years. He's a fellow entrepreneur and innovator, fellow lecturer as well, downtown Toronto. He's also a great client of ours at Macro Design and Event. So, Steve, it's great to be here. Now, I know that there's also lots of students tuning in, but also lots of hardware innovators and inventors out there tuning in. People with ideas in IoT technology, connected tech, wearable tech, water products, or even just regular home inventions. So, Steve invited me here today to talk about how inventors, just like you, take their hardware invention ideas from just that idea that's brewing in your head to a commercial product that's on store shelves or even online in places like Amazon, Shopify, etc. So, first and foremost, I want to talk a little bit about the hardware industry right now, especially in connected tech, wearable tech. It's almost what I would call the perfect storm of opportunity for new product startups. And I've got 6 key reasons as to why. And first and foremost, over the next 20 to 30 years, whether you love it or hate it, everything you see around you will be connected with a chip in some way or another. So much as the chair that you are sitting on is going to have a microchip in it that's going to let when the cushion needs to be replaced, or obviously more complicated things like we know right now, like the Nest thermostats or the watch that you wear on your hands, or of course Steve innovating on all kinds of things like headgear and all the rest. But look, one thing is certain: that connected technology and biology and software are all merging together. And it's happening right now at an incredibly accelerated rate. So, for those innovators that are coming up with a new way or new evolution to connect this is really almost like what I would call the next big, essentially industrial revolution. But it's the industrial revolution of hardware, software, and biology coming together at once. And that's happening right now. And that's going to evolve over the next 20 to 30 years because everything you see around you is going through a redesign. And it's the innovators like you that are sitting there on this call. You folks are the ones who are going to be doing this. Because one of the second things that I want to mention, which is incredible that's happening right now, is big companies, the giant corporations in the product space, they're spending less money on internal research and development, but they're spending a lot more money on acquiring small hardware startups. The model has changed. It's changed to the point where now they're looking for the world to come up with the next big ideas. The world to come up with that Nest thermostat, Oculus Rift, Scrub Daddy, or even I think of our own clients like Petbot, GoFish, Moonlight. They just come up with the ideas, get the product designed, engineered, get some sales of that product. Then the company comes in and says, well, that's fantastic. We can make it 100 times the size, and creates a great partnership deal for both parties. I want to add to that, especially because we're talking. I know Steve is a professor at the University of Toronto. I'm a lecturer at Ryerson University. And I'll tell you, when I started my business in Mako Design 20 years ago, there was hardly any support for entrepreneurship, whether in the academic setting or whether just in the general setting for the general population. Right now, versus 20 years ago, there are 100 times more incubators, co-working spaces, accelerators than there were 20 years ago. This is a huge number. Everywhere you look, if you're anywhere near a major city, you'll notice dozens upon dozens upon dozens of institutions at government levels, at private levels, at school and academic levels that are there to help companies get off the ground, go from idea to production. So there's more support than ever before. In terms of hardware, there are more product design tools now than ever before to make it easier, faster, quicker to actually design, engineer, and prototype. The CAD tools that we have now have such advanced simulations. It makes it easier and quicker to create great quality products. Steve's product that he's introducing today is something that happened in just a few weeks in terms of at least the encasing side, that sort of stuff. And as you'll see, Steve's got some incredible technology that he's going to be releasing later. But that just goes to show you something that never could have been done even 10 years ago, let alone 20 or 30 years ago. But right now, because of the new prototyping methodologies, the materials, then the CAD software, and as well as a lot of intellectual capital around that, it's easier than ever for a hardware product to go from that idea through to actual real prototyping, test it, and then get that thing to market. And then fifth, this is a big one. It kind of aligns with what I'm talking about in terms of tools and prototyping, but additive manufacturing. Additive manufacturing is a huge emerging technology that's coming out to allow startups to go to market with just 50, 100, or 200 units of their product, to test it, to get real buyers to actually purchase the product, and then get real users to actually give you feedback on how great your product is, what they liked about it, what they didn't like, allow you to tweak, adjust, adapt, and then come up with something really great when you actually decide to tool up and go to a full production run. Additive manufacturing is getting less expensive, more localized, and with a massive range of new technologies and new capabilities, both on a materials and a technology perspective, to actually get those products made and into real users' hands. And the last thing I'll say, which is really important right now, making it easier than ever, especially in the consumer product space, is crowdfunding. Kickstarter, Indiegogo, Shopify, Amazon. Never has there been so many tools to get you directly from the manufacturer or from you selling directly to end consumers. And crowdsourcing is incredibly powerful when you look at Indiegogo and Kickstarter, because you can pre-sell your units based on a prototype, pre-sell that design to real buyers where they're pre-purchasing these units to help you pay for your production run going forward. So that is a really big piece to the puzzle. And, what I really want, as well as hardware startups, to understand is, especially if you're at the really early phases, you've either just got that idea, or maybe you've worked on some intellectual property, or maybe you're creating some new technology that you think is going to be useful. The most important thing for you to keep in mind is that when it comes to consumer products, there's really only one way for them to become successful, and that's to get real units into real users' hands that have purchased those units, and to get feedback on those units. It doesn't have to be a lot. Like I said, it could be 50, 100, 200 units. But the important thing to understand as a startup is that whether you're going to invest in that to get it to a manufacturing standpoint, or whether you're going to get an investor on board, or whether you're going to look at other options like licensing or partnering up with a bigger brand to do that, know that the end game for a consumer product is real sales. So there is no shortcut in hardware. And that is key. If you understand the goal, and you understand your pitch, that will help you all the way right back to your ideation phase to figure out what are the steps to actually take that product to market. So the last thing I'm going to leave you with is a quick end to end when it comes to hardware on how you actually get that product, develop it from that idea that's in your head to a real manufactured unit that's on the shelves. First and foremost, you identify the opportunity. I'm sure many of you that are on this call right now, you have that opportunity. It's in your head, you're working on it or whatnot. But for those of you who don't, I just want to say a quick thing here. Those who saw it, they've got lucky. I mean, once or twice, maybe 3 times in your life as an inventor, you're going to see something that really is a major market winner. And absolutely, first and foremost, you should jump on that. If you have had that luck or that blessing that idea has come to you, then it's almost your responsibility to jump on that, because you could help thousands, if not millions, of people around the world. But if you haven't seen that idea yet, the best advice that I can give is just keep your eye out in your day-to-day lives, at work, at home, whatnot. Look at things that inconvenience you directly. Look at things that are inconvenient to you at work. Look at things that are inconvenient to you at home. And when those things happen, and it'll happen a lot once you really start to open your eyes to it, once you look around for those innovations, you will notice that they will pop out at you and you will recognize them. Now, when that happens, when you see that inconvenience, 99% of people out there, they'll see it, they'll get frustrated, they'll move on. But when it happens to you, the listeners on this chat today, all you have to do is ask yourself, how could I solve that problem? And I'm not saying that it's going to, the first time you're going to come up with some great invention, but the reality is if you continue doing this throughout your life, throughout your career, throughout your personal life, the innovations will come, especially if you prioritize this top of mind. So now let's assume that you've got the idea. You've either come up with it already or you're working on it. The easiest thing you can do is just simply sketch it out. It doesn't matter if you're an artist or you're an engineer, whatever the case is, just grab a pen and paper and sketch out that physical concept. In conjunction, write down what it does. Who is your customer? Who's your ideal customer? And how is this product going to provide value to them along with that sketch? It's the easiest thing that you can do. You can do it at home, and you can combine that with doing some research on Google and just look at competitive products or look at designs you like or designs you don't like, and just at a very preliminary level, just map out how you see this product working, how you see it, envision it. Keep in mind, you don't have to flesh out all the details. That's what designers and engineers are for. But if you can flesh out what you want it to do and kind of how you visually want it to work, just in a very basic preliminary level, even just literally sketched on a napkin. And believe it or not, we got a lot of clients that come in with just a sketch on a napkin. It's not a cliche, it is a real thing. Even if that's all it is, that's enough to at least provide enough merit and enough value for you to then get really powerful and strong advice as you go forward with your actual design team, which leads me to the next phase. That's industrial design. Industrial design is a combination of visual design and hardcore engineering. They sit somewhere in the middle. It's somebody who designs out the aesthetics, but also figures out the features and how they're actually going to be built in CAD. This is a CAD design phase using CAD stands for computer aided design. This is arguably the most important step. This is essentially the foundation of your product. This is where you want a number of very senior designers and engineers to figure out essentially 3 critical things that form the foundation of the entire future of the product. 1 is the key features. 2 is the visual and cosmetic look. How does it actually look? How is it going to look in real life and render it all up? And then how exactly are these things going to physically work? What is the underlying engineering? Which then leads us to our next phase, mechanical engineering. Once you're done all your design and you love it and you figured out how it's going to work, now you go through in detail all the tiny little bits and pieces of that industrial design. If there's electronics, that's when you're actually building out your rough PCB board, doing your firmware programming, you're putting all this stuff together, which then leads to the, let's call it rough quasi-working prototype, generally done in 3D printed materials. Could be a boards off the shelf or custom PCB, whatever else. You're putting that into a rough prototype to try to actually physically test how this thing's going to work. The rough prototype then leads into refined prototypes, which then lead into test prototypes and then pre-production prototypes. Real prototypes that nail down every single detail almost to a manufacturing spec before you then do the final step, which is taking it to a manufacturer, ideally with it fully vetted out, your bill of materials, all your engineering specs, the final finished, fully functional prototypes of the product, so that a manufacturer can then quote on the production. And that is essentially the development side of how you go from sketch to production. And of course, after that, there's all kinds of things that go on in terms of actually selling the product and building the business and scaling and design iterations and all that. If you are interested in the hardware product development space, I'd highly recommend you check out the podcast that I run. It's the Product Startup Podcast. It's the hardware development industry's leading podcast about everything from initial idea to patenting to sales and marketing. All different types of things from wearable tech to green tech, et cetera. It's all baked in there. And if you're actually interested in getting a professional firm to help develop your product, of course, feel free to reach out to me directly on LinkedIn. Anybody who's on the call today is welcome I'll add them back on LinkedIn for every single person who mentions that they came through here today with Steve's show. And of course, if you want to reach out to our firm, it's just Mako Design, MAKO design.com. Thanks again, everyone. Much appreciated.
Yeah, thanks again for an excellent talk. Very, very inspiring. We're kind of in a new industry. There's a whole bunch of new industries coming out now, from wearables, water technology. I think this intersection between humans, water, and technology is probably going to be a very big industrial sort of trend. And so I think, I think we're onto something quite epicentral here. And I think it's interesting. I think Toronto, Ontario is kind of where a lot of this started, where these wearables started in the 1960s and 70s, and where water and humans and technology intersect. And I think it's really good. We look forward to creating some interesting design collaborations. Kevin will stay in touch, and we're going to hopefully see some important developments here in Toronto.
Beach time.
Okay, so now it's beach time. So whoever wants to join us for an ice water swim with the underwater augmented reality eyeglasses. So we got all these crazy technologies that we're building here with the underwater camera, and the underwater computer, and underwater augmented reality, and underwater heart monitors and physiological monitors. And so we're entering a new era, and we're going to have a fun cyborg ice water swim. And ice water swimming is a long-standing tradition that brings lots of health benefits. I've never tried cocaine, but a lot of people who've done the swimming say it's a lot like cocaine, the buzz you get from it, but without the same risks of heart damage. Like you have, instead of destroying your heart with drugs, you can make your heart stronger by cold water swimming. So it's a great kind of health force. It's a great, there's lots of literature been written about it. It's great for physical, affective, and mental health. And so we're going to go to Ontario Place Beach. We call it informally the Teach Beach, because the beach has no name. It doesn't show up on any maps, and we call it the Teach Beach. And so we have about 560 members of Swim Up who swim year round, and some of us are going to be there to play in the water with a bunch of augmented reality technology. So we'll break briefly for our lunchtime break, kind of an extended lunchtime break, enough time to get down to Ontario Place, get in a nice swim, get changed out, and come back, and we'll reconvene at 2:40 p.m. So thank you to everybody who's participating, and we're going to be live streaming the ice water swim. So if people if you can't make it, join us, and we'll see you all back soon, and we'll see some of you online, and we'll see some of you in real life at the beach. Swim, we got lots of good things working. We had the heart monitor working so I've got my ECG electrodes running, and we're streaming live heart data and monitoring. And so we're able to, with the Smart Swim, you can see a GPS overlay, map coordinates of where you are, and so what's happening inside your body and what's happening around your body. And this is a beautiful example of environment, and environment. So you get to see what's happening inside your body, and you get to see what's happening around you as well at the same time, so you get to see your environment and your environment. So that was really, really fun. And we had a good turnout. We had the outdoor classroom there. So we met on Ontario Place Teach Beach. It's kind of like a secret beach that nobody knows about. It doesn't show up on any maps. It's not listed anywhere. So we just call it the Teach Beach, and we built an outdoor classroom there. So that was quite nice. And so that was a good example of this boundaries between, you know, human, water, and technology. And we had a good chance to hack together some nice demos and make things work. Thanks to all the people who helped out, you know, Caden and Perry and everybody else who helped make this event a success. We got Swim Drink Fish was out there too with the water sampling, testing the water quality. So that was really good. And I think these concepts are getting more and more important. So now at 3 o'clock, we're going to hear from Stanford University, the world's smartest toilet, a smart toilet with all kinds of sensors and everything that monitors health and detects COVID and this sort of thing. So you can imagine toilets, you know, in the home or in sort of in industrial settings or wherever, commercial facilities, where you automatically get this. Oh, here he is, right on the call. It's great to have you. We're looking forward to your keynote at noon your time.
Thank you so much. Yeah, it's at 3 o'clock over there, right? It looks like it's really cold over there.
Yeah, it's about minus 5 degrees, and the water temperature was 3.2 Celsius, and we had a really good swim. We had a good turnout for the swim. Lots of people came out to try the augmented reality underwater sensors for the swim. So we had the smart glass, you know, and people could see their heart. We could see our heart waveforms plotted, obviously the heart rate plus the waveform, and see all that material plotted in real time while we swim, as well as knowing where we are, GPS coordinates, kind of safe swim technology. And so that was really good. And we had a good series. We had a good series of morning sessions, and lots of technology. Like we talked a little bit about some of the historical aspects of WaterHCI starting in the 1960s and 1970s with the sequential wave and printing machine to see underwater sound waves and so.
It looks like a WaterHCI. It looks like a WaterHCl. It's a hydrochloride water or something.
Yeah, actually it is. It is. Yeah, that's a good point. Like we need to sort of, how do we say, yeah, maybe fluid. Well, we for a while we talked about fluid user interfaces, or fluidic user interfaces. Those were terms we were using years ago. Now to generalize beyond water, because we also were looking at other liquids and how they interact technologically, and also air jets like this underwater pipe organ can play with blasts of air coming through it. So now you have air as a fluid user interface. So it's more general, perhaps.
Very good, very good. So can I just check whether I can share my screen just before the talk?
Yeah, that's a good idea. See if. Yeah, you're live, by the way. We're live, but that's okay. I think, you know, we should have some fun. Let our audience see a little bit behind the scenes as we prepare.
Okay, so let me do this.
Looks like the sun is shining there. It's a nice warm day there.
Yeah, it's not that warm, but it's more like, you know, how can I say it, 50 degrees in Fahrenheit, and so around like a 12 degrees Celsius, 13 degree. No, I think it's more than, yeah, it's a 13 degrees Celsius.
Yeah, that's not bad.
All right. Can you see my screen?
Yes, I can see it. It looks beautiful.
Thank you. So, yes, I'm gonna hide it. Oh, how can I go up? Hide. All right. So I think, yes, it's me again.
Beautiful. And then are you able to record your talk while you stream? We'll record it here, but if you record it on your end, then you'll have a higher resolution recording than what comes across.
Yeah, how can I record it? That's going to be a
Okay, if it's too much trouble, don't worry about it. We'll just record it here.
Let me see. I'm pretty sure I can. Yeah. Oh, yeah. I found it. Yeah, I found an option.
I usually use OBS or something, but whatever works best for you.
Okay. What? It says a upload to the Dropbox.
Yeah, okay, well, we'll just record it at this end if it's too much trouble, if it's not something you're familiar with.
Oh, okay. All right. Thank you so much. I really appreciate that. Yeah.
Okay, you might as well get started. Yeah, take it away. If you're ready, start whenever you're ready. And we're all looking forward to
Can I
this.
start it right now? No. I think we have to wait until like 12 o'clock or something, right?
Yeah, if you want. I don't know if you want to start early. It's
Is it okay?
Yeah, just go.
I don't
Yeah.
mind. Yeah.
Yeah, you can just get started whenever you're ready.
Yeah. So I can start. It's just a window. Yes. Share full screen. All right. Can you see my screen? Yes. All right. So yeah, it is my honor and privilege to share my work in the 23rd annual Water, Humans, and Computing WaterHCI DECONference. My name is Seungmin Park. I'm an instructor of urology at the Stanford University School of Medicine. Um, Before joining the Department of Urology, I used to be in the Department of Radiology for last 7 years. I used work for Dr. Sanjeev Sam Gambier, who's the chair of radiology for last like 12 years, and he was a truly amazing scientist and physician. He's the one who actually tried to revolutionize in the healthcare. So he passed away last year because of cancer. And it is kind of unfortunate for us because he was recognized as the pioneer in terms of early cancer detection. He was the true leader of radiology that he was able to diagnose variety of cancer. But ironically, he passed away from cancer because he was not able to diagnose his own cancer. And he proposed a really revolutionary the concept in the field of medicine, which is called the precision health, which I will explain here. So this talk, I'm gonna introduce about why we're working on this specific area, background and motivation, especially about the precision health. Then I'll actually change my topic to the excreta-based diagnostic system, which is majorly actually performed in the water, toilet water. And then I'll give you some research summary and acknowledgement to the work. So first, just want to introduce precision medicine prior to the precision health. Precision medicine is a one of the um, one of Barack Obama's initiative. So he believes that because everybody is unique, so every treatment to the disease has to be unique to a person. So what if we figuring out the right dose of medicine was as simple as taking our temperature? So that's going to be depending on who you are. So we value a personalized medication, personalized treatments. So this is the basis of the precision medicine. This precision medicine initiative was funded by the Barack Obama administration around like a $350 million, and Dr. Eric Topol from Scripps Institute, he's the head of this initiative. But nowadays, it's more important to think about the before, you get ill. I mean, if people get ill, precision medicine will provide the right treatment for you. But precision health is slightly different because precision medicine is regarded as a reactive approach to the disease treatments or intervention. But precision health is more proactive. and personalized healthcare that's focuses on prevention and early detection via longitudinal monitoring of an individual. So as you can see in this diagram, Dr. Sanjeev Gambhir convinced this idea like a long time ago. So he believed that even a person is in his mother's womb, we can do genetic screening. We can take a look at the family history. We can take a look at the socioeconomic factors of a person, even a person is even before a person is born. Then, based on those assessment, we can give him a like a risk assessment at all stage of life. So, based on those risk assessment, we can provide a customized monitoring tool. This customized monitoring tool will generate tons of data every day. Then it can be fed into the integrated health portal where the data analytics and the proactive intervention happens. So data analytic includes a pattern recognition, machine learning approach, predictive modeling, and digital twin and actionable response determination. So in order to deploy successful precision health concept to the world, low cost, repeatable, and reliable technology are required. So this is how Dr. Gambier envisioned that it can be performed in the home setting. So passive monitoring is one of the important key because if you need to increase the user acceptance or user compliance to a device, they will eventually not wear the device. Such as your let's talk about your smartwatches. Smartwatch actually give you really great deal of human health data, but one of the limiting factor for that is because if you want to measure like a CKG or EKG or something like an electrocardiogram for yourself, you have to actively engage to the smartwatch. So Dr. Gambier envisioned that passive monitoring is one of the key aspect of precision health. So as you can see, we have automobile. We can embed sensors over there to look at the what's the style of a human over there, like a driving style that will tells you about the vital signs, stress, or environmental factors. In the bedroom, you can set up a sensor to the bed so they can actually see how like a degree of the sleep you have last night. Of course, you can have like a medication compliance, or you can even actually take a look at the refrigerator with using your smart glass to look at the dietary habits and the food imbalance or something like that. But one of the most important aspect of this application is your bathroom. So you can utilize of the saliva with a smart brush, or you can use a mirror. We can call it wise mirror that's look at your cardiometabolic features of your facial expression, or even your weight. I mean, this scale has already have like different functions such as measuring your body fat, measuring your body mass, muscle mass, all those kind of stuff. But one of the most interesting thing that can happen is in the toilet. So we're trying to focus on the urine and stool because nobody can avoid it. You have to go to the restroom. You have to at least generate human excreta almost every day. So if we can utilize any kind of health information from those human excreta, it will be very, very useful. But there's a kind of associated cultural taboo, or we can even call it some of like a limitation in dealing with the human excreta. That is the limiting factor to utilize human excreta as a diagnostic tool. We just simply flush it that away. So it's kind of shameful. So we're more interested in the digital biomarker, so which can be defined as physiological, biochemical, and behavioral data collected by the smart devices. So it's inherently quantitative. It can be collectively analyzed with a predictive modeling, and it can be used for health pattern recognition. Even from that, we can do some actionable response determination. So, what kind of response can be determined by based on these digital biomarkers? So, one of a great example is a recent research that was performed at Stanford. Dr. Michael Snyder, who's the guru of this digital healthcare, he just published a paper by using smartwatch data to predict the COVID-19 screening. So it's a great actually amount of attitude toward to the those kind of wearable technology. But as I mentioned, there's almost no such technology in bathroom because because the human excreta usually excreted in a way like natural way, so you don't have to worry about like getting blood from your arm because it's just naturally excreted. If we collect those information to use as a digital biomarkers, it will be very helpful in terms of managing one's health care. So we envision that the digitization of the events, any kind of event, will lead to the digitalization of disease management, and it will eventually get into the digital transformation of healthcare. So we believe that ultimate digital biomarkers can be biochemical parameters of your human excreta or any kind. I mean, any kind of human biofluid. So it includes automatic sample collection, sample preparation, recognition, amplification, and transduction. And the lastly will be the integration and the instrument design. But one of the most challenging part is the sample collection. Think about your toilet. It's a very narrow, very small device that can be mounted onto the toilet. So we have to think about the clever way to avoid this laborious, sample collection processes. And I will introduce you very soon. So based on those data, like a future data we can collect it from the toilet, we can establish a human health model. So I have a grand hypothesis on it. So based on those human health model, we want to use the time derivative of those digital biomarkers. So time derivative only can obtained by the longitudinal monitoring of a multiple human health factor. So the gateway for that is a smart toilet because it can be performed in passive way so that the it will not interfere with any kind of normal human behavior in the toilet. So we can accrue data over like a large amount of time so that we can actually establish a very accurate human health model. So I'll talk about the excreta-based diagnostic system in your toilet. So this is one of a representative image that we're thinking about. We're trying to utilize artificial intelligence. So and talk about the like the connecting to the IoT. So it's the IoT device, and we're trying to analyze in situ and in real time. So luckily, this paper was published last year in Nature Biomedical Engineering, and which garners much attention from globally. So we have this paper has been tweeted for more than 14,000 times, and it actually scored ranked number 7 in terms of altimetric media attention score of among all published articles in 2020. So and as you remember, Dr. Ray Topol, who was the leader of Precision Medicine Initiative, he kindly introduced my paper in his tweet, and I sent him an email for acknowledging his kind introduction, and he mentioned that it is a landmark paper in terms of precision medicine and precision health. So I'll talk about the precision health toilet, smartest toilet that, as we claim. Um, in order to engage like a huge population to this kind of precision health scheme, we believe that the toilet format has to be mountable and affordable. So it should not be like using a pipe or using some different devices or like changing the whole toilet for monitoring human excreta. So we think that the mountable format will be the desirable format for wide deployments of this precision health toilet. And it has to be related to the excreta measurements. So one of the counterexample is from the academic research group from Rochester Institute of Technology. They just received a Series A funding for the commercialization of their approach. But what happened is they do not measure, they have a toilet, but they do not directly measure the excreta. What they measure is they measure the electrocardiogram from your butt, which is kind of clever, but it's kind of great addition to the what we can measure. But the thing is, it's not directly related to the human excreta. So that's kind of a limiting factor patient. So as I mentioned, passive monitoring is a key. So we don't want to introduce any kind of stepwise, functioning. So if a user wanted to monitor their own health, what we're trying to do is it's a completely passive. So they don't even know they're kind of monitored. So that's going to be our like a third criteria. And fourth is a clinically applicable, actionable data gathering. So we're trying to make it actually as much as clinically applicable and actionable. And fifth, it has to be connected to the health portal. So we're trying to use a IoT as an infrastructure. So this is an example how we implement it. So first, we are using urinalysis. That's really simple one. Computer vision and 10 biomarker detection can be possible. And second is a uroflowmetry. So we're using again the computer vision to measure the urine volume, speed, and duration. And third is a stool analysis. We're trying to use machine learning, not the human effort on it. And they can determine the stool morphology and liquidity nicely. And fourth is I'll talk about how we integrate the system for providing a personalized healthcare solution. So, so we have an analog biomarker, which is directly opposite to the digital biomarker that is recorded by a user or patient for their own subjective interpretation of what happened in your toilet. So this is called the Bristol stool foam scale. So it can be classified into the 7 different classes, and it's a diagnostic medical tool designed to classify human stools into 7 classes. It was used for diagnosis of the IBS, irritable bowel syndrome, or it can be used for therapeutic evaluation for chemotherapy responses. And it is developed by the Bristol Royal Infirmary in 1990s, and it's composed of everyday language so that the doctor actually can give you this kind of card so that you can compare directly to your stool to this. But one of the biggest issue is that there's kind of recollection bias, and second, always it's kind of always that the professional analysis is way better than the patient or the user analysis. So what we're trying to do is trying to digitizing these events. So I first employed the Google Inception V3, which is deprecated nowadays. So I'm actually trying to use a ResNet, which is more advanced version of the deep convolutional neural network. And this architecture was devised in the ImageNet competition 2014, and it was trained on 1.2 million image set, and it was trained on the over more than 1,000 categories, and it has a really small error rate, 6%. And one of the most beautiful feature of this Google Inception V3 is that transfer learning is available, which means we can just swap the last layer of trained architecture for our own purposes. So what happened is they already have this kind of architecture publicly available. So you can put the like a random flower image, and they will determine which flower you're looking at. So in this case, Daisy has a score of 99% of accuracy, or it can be sunflower from like a 0.5% accuracy. So similar to that, what happened is we just swapped the last layer of training set to our stool images. Okay, so stool image, how can I earn it? So I mostly acquire from the web search because there's kind of really wealth of those images in like a Reddit or in like a Twitter. So I acquired 2,364 image sets. Currently, I have a more than 20,000 images for training. And the thing is, train the machine by myself by providing the ground truth for this image, but I specifically invited two colorectal surgeon who were trained on such task. I mean, Bristol stool classification. So what happened is we have a really great, match rate for the machine. So algorithm is represented by this green dot. No, not green dot. I mean this blue line, and the red dot is medical students who were trained on. So you can see that test set is very comparable to their performance. So this is a hardware part. So I mentioned, it can be device as a mountable format. So we have LED strips with a pressure sensor on the bottom, so that we know when the user sits on. And we have a really small computer which is called the Raspberry Pi, and we have a camera module on it. So this is the example of how we installed into the toilet bowl at Stanford University. So this is the actual image. So we have a pressure sensor here. That pressure sensor lead is very simple. So we can measure the total sitting time of 129 seconds here. And after measuring it, we accrue the image from the clean toilet seat to the toilet paper within it. So we deploy the first model of our. Yes. Oh, sorry for that. Can you see my screen well? Okay. So just let me know. Yeah, just stop me whenever you cannot see anything. So I'll be, yeah. I'll, how about it's PowerPoint view. So I'll share. Give me one more. Does it okay. Does it work? No. Does it work? Is it better? Is it full screen? Okay, I did it, but it hasn't reflected it. Okay, so let me turn off and turn it on again. Okay. Window, share. How about now? Yes, I'm on the page 20 right now. Can you see it? Interesting. Okay, so I'll use this scheme because I think something is not working. Yes. So what we did is a first layer of our CNN architecture has four different classes. So we want to detect the clean bowl state and the urine only state and the stool only state and toilet paper state. So what we can measure is, interestingly, we can measure the first stool dropping time, which is directly related to your gut health function. So it is like a prime importance for the elderly people. So we can measure the first stool dropping time by just chasing the image from the clean state to the stool state. Then we can measure the defecation duration for 80 seconds by measuring the time, first stool dropping time to the first toilet paper got introduced to the toilet bowl. And after we determine state belongs to the stool state, what we do is we introduce to the second layer of our deep CNN, which spans at seven different classes of stool. And as you can see, it's constantly talks about the Bristol Stool Scale 4, which has a right determination of the stool image in the toilet bowl, like a sausage or a snake. And as you can see here, it looks like a snake here. So we actually tested for 21 participants for 55 application events, and you can see that they have a discrete pattern of their excretory patterns. And we have a really great match rate. So our CNN has a great match rate to the surgeons, the classification, overcoming the match rate between the user and surgeon, which is like a 20% less. And as you can see, we can even do the longitudinal monitoring of a human health, so that the red dot is indicate a human participant who chronically suffering from chronic constipation, while this blue dots represented what is that, the patient with the chronic diarrhea. So he or she may need an anti-diarrhea medication. In this case, for the red case, she or he may need a stool softener or serum. Or one of the most interesting participant here is one of a thing that goes back and forth with chronic not constipation to the diarrhea in like several days. In this case, it may be the participant may be diagnosed as irritable bowel syndrome. So this is one of example how we perform the analysis. This is the raw image, and this is a computer vision, how computer vision is envisioning it. So by seeing that, we're using the active segmentation of a human stool, and this is how we extract the color directly from it, and that colors of poop can be used as one of the diagnosis tool. And of course, because the user will not mainly use their like a singular toilet in their home, right? If a user has to go their work, they're using different toilet. So what we did is we deploy the smartphone apps. It is available in iPhone and Android, not yet for publicly, but we're trying to release it as soon as possible. So you can, by using this, if you don't have any toilet nearby, smart toilet nearby to you, then you can use the smartphone app. Just take a photo manually, and it will actually do analysis by automatically. The second module that I'm going to introduce is a uroflowmetry. So uroflowmetry is very interesting. So this is one of a Stanford Euroclinic utilizes. It is called a uroflowmeter with a spinning disc principle. So what happened is they have a funnel here. So that male has to stand and the pee directly on top of the funnel, and the female has to sit on top and directly urinate on top of this funnel. So what happened is they have a spinning disc in the bottom of this device. That spinning disc has a like constant rotating speed, but it will be slowed by the urination. Then we calculate how much speed was reduced because of the urine. Then we can actually estimate the urine volume, max flow, average flow, and stuff like that. But one of the challenging part of this application is it's extremely hard to integrate those spinning discs to your ordinary toilet. So what we're trying to do is trying to use optical vision, computer vision again. So based on this, so we use a two camera system. Then we just reduce the, by using computer vision, we can subtract all the background image, and we can reconstruct it as a 2.5D image, and we use the triangulation to calculate the volume of those urination. And then the result is amazing. So we have a conventional uroflowmeter represented by the blue line here, and our computer vision is by the red dot. It has almost like a perfectly fit to each other, and we calculate how much overlap, and we have a Pearson R value in terms of duration is a 0.96, while the volume wise we have a 0.92 accuracy. And other like the factor we have urinalysis. Urinalysis is basically a dipstick analysis. So we're envisioning that we can employ like this way. But I consulted to the one of the bidet company, and the bidet company has like a biggest concern of getting wet straight back to the housing because it actually caused a lot of waterproof problem, and all those like an engineering issue we have to resolve it first. Lastly, but not last but not least, because your toilet will be shared by your roommates or housemate or your family member. You have to know who's using the device. So we're trying to use a flush lever as a biometric identification method. So this is one of the method that I can introduce. It's a really cheap. It's $18 fingerprint scanner that's available from Amazon.com. I just use a 3D printer to use this as a like a flush lever. And when you actuate this, your identity will be annotated. But one of the concern here is that the most advanced toilets nowadays available by Toto or Kohler, they do not usually have this flush lever. They have an automatic function. So whenever a user left the toilet, they automatically flush it. So to overcome those issues, and other issues may be that if you cannot flush by yourself, then somebody else can do it for you. Then in that case, some kind of mixture of identity will be happening. So what we do is we devise a little bit of way that use a human anus as one of a biometric identifier, because human anus is known to be very unique to a person, according to the famous painter Dali. Salvador Dali, he actually convinced that this idea by inspecting human anus for more than 30 people, saying that it's a very unique to a person. So we utilize this function. So no matter what, you have to expose your human anus to the toilet, and if you have like a one more sensor over there, and as you can see, we just use a three different computer algorithm to predict who's using the toilet. We have like more than a 95% accuracy to infer who's using the toilet. But as I mentioned, this can actually cause a lot of ethical issue and privacy issues. We're still actually thinking about it, and currently I'm working on the IoT architecture so that all kind of the privacy breaches to protect it. I'm gonna use Amazon Web Service because they have a really great architecture that can they can protect like effectively. And as I mentioned, because smart tool we're using the camera as a sensor, so that's is very similar to how can I say as a spy cam in the toilet. So what we need is we need to measure the user acceptance. So this is very biased survey, but I want to share my result. So this is a survey taker from the Stanford community, and we have almost 300, not almost, I mean 300 participants. Then, as you can see, it's a highly educated population. More than almost like a 40% has a doctoral or professional degree. And the ethnicity wise, it's a white, and we have like a dominant, a second dominant as Asian. But interestingly, we have a very favorable result. I think it's because they may actually recognize this as a research effort, but we may, if we actually frame it to the different like a consumer electronic, we may have a different result. But well, more than 50%, like a 52% is favorable, 20% is kind of indifferent toward to us, 30% is kind of not to our system. And interestingly, statistically, there are like a non-camera base has more favorable toward to the user acceptance, while the camera base is least favorable. I mean, as you can imagine, anal print is most like abhorred by the user. But we ask another question: what if we replace the camera with a different sensor, such as like different like an infrared sensor or like a laser scanner, which allows to us which allowed the non-reconstruction of the anus as an image. Then 70% of rejectee that they agree with us to use the system. So to advance this technology, I'm working on more like pregnancy, STD, street drugs. We want to incorporate all of those, and we're trying to include the guaiac occult blood test on it, and the microbiome is another target, and like obviously we're actually seeking a funding for the COVID-19 detection. As you can remember, there's a wastewater study to detect the COVID-19. So by this effort, we're actually trying to propose this coronavirus integrated diagnostic toilet, COVID ID toilet, and we talk about some of the ethical issues. So, because of the time limit, so I just want to close this talk by acknowledging my mentors. I especially thank for my mentor, late mentor, the Sanjeev Sangambir, who passed away. I really missed him, and this is impossible with all this collaborator. If you have any question, I'll take it. Thank you very much.
Honor to have you here among our Water Humans and Computing Interface conference. And yeah, so are there any questions regarding the world's smartest toilet? Let's check the live chat. Is there anything coming up? And also, I just want to remind people that feel free to post questions to the WaterHCI website, WaterHCI.com, because we'll come back and we'll continue this discussion online. And I'm sure the speakers will be happy to answer questions on their online forum after we have a Facebook group and discussion group, as well as the conference site itself. Okay.
Yeah, are any smart toilet in operation publicly? One of the question that I received, and yeah, interestingly, there's no such toilet for the human health monitoring yet. I mean, there's a kind of some of those. I mean, there's like a Toto's, intelligent toilet introduced in 2008. They have like a urinalysis function, but the cost of those toilet is a $6,100. So kind of people's kind of not actually buying it, so they discontinue it. But please take a look at the CES 2022 this year. Total will actually unveil some of their healthcare toilets soon. So it will be publicly available next year, and we're working with some of bidet company to make it, publicly available next year.
Great. That was really good. I think where this will really make a big difference. I noticed when you see automatic flush toilets, they didn't first enter homes. They first entered kind of commercial installations. That's where people have the budget and the wherewithal to design these things. So I'm imagining this product might find itself, in kind of more commercial installations first, perhaps, who knows. But you could imagine if this was more widely deployed, it might be something to manage the COVID outbreak, in the sense that if you're able to detect COVID-19, maybe you'd have something that would notify you if you had illness. And in any case, I want to, it's a very, very excellent talk, very thought-provoking, and I think we'll have more and more discussions. We had a lot of discussions in our DECONference 1999, DECONference 1999, DECONference 2000, and DECONference 2001, when we had the sensor-operated shower. We built the world's most advanced shower. It had a 6-column shower with 6 stations, and it had 6 depth cameras in it, one for each person. And we actually had a graphics card for each shower station. We had 6 graphics cards in one PC, one computer, and we built
created the world's first GPU using graphics processing chips for parallel processing, came out of that smart shower. And that work ultimately led to work presented on Capitol Hill in Washington, D.C. It also led to the creation of OpenVidia, the project, which is kind of a predecessor of CUDA, a parallel GPU. So it was a lot came out of that project, and so a lot of these things lead to in further directions that we might not even imagine in terms of what new discoveries are made. I want to now transition to Mark Matson, from the founder of Swim, Drink, Fish. Mark is my inspiration for this taxonomy. We came up with this taxonomy, which we call the interface taxonomy. And it was largely inspired by Mark's thinking, whether he knew it or not. His stroke of genius in naming the company Swim, Drink, Fish takes us into the idea of, we all thought, oh, wow, that's really deep and insightful in some way, because when you swim, you go into the water. And when you drink, the water goes into you. And we thought, okay, and then when you fish, you're separate from the water. So we thought, okay, there's these 3 different ways you can interact with water. You can put yourself in the water, or you can put the water into yourself, or, of course, the water can come in and go out, and of course, in terms of the talk we just heard. And then the last category is where you're separate from the water, where you have, if you're going fishing or sunbathing or meditating by the beach, we have a lot of people just sit by the beach and enjoy the waves and so on. And so with these 3 ways of interacting with water, and we have the 3 ways of interacting with technology, you can have the technology like surveillance that's watching you, or you can put the technology around yourself like smart clothing, like these smart eyeglasses, or you can put the technology in yourself. So when you enter into a vessel, you become a cyborg. Manfred Klein's coined the term cyborg, and the example that he used as a person riding a bicycle is his favorite example. When he was talking to me, a good friend of mine, we talk about this, and he said, hey, the best example of a cyborg is someone riding a bicycle. And I said, well, what about someone on a boat? Because that's equally, because bicycles are only 200 years old, but boats have been around for more than 1 million years. Boats have been around longer than Homo sapiens have been around. So the very first cyborgs were perhaps the predecessors of Homo sapiens in boats. And so when you're on a boat, it's a cyborg extension. So when you're on a boat, you enter a vessel. When you have implantable computing, like implants, the vessel enters you. And then the third possibility is the technology is separate from you, like surveillance. So we have surveillance, where the technology is watching us. We have surveillance, where we are a cyborg and we enter a vessel, like smart clothes or a smart boat, or a bicycle, or smart eyeglasses. We call that surveillance, from the French word sous, under, meaning in English undersight. Surveillance is oversight. And then when the technology enters us, implantables, that's what Katina Michael coined the term uberveillance to describe that. So we have these 3 things. And then it's the same with the water and the technology. There's 3 ways that those can interact. The technology can go in the water, like you have the smart buoy. Steve Halford and I put that smart buoy in the lake to monitor the temperature of the lake, for example. That's putting technology into water. Or the water can go into the technology, and that's your smart plumbing, sensor operated valve, smart toilets, where the water flows in through the technology, or the 2 can be separate. So again, we have these taxonomies. So it's very much an honor to speak to Mark Matson, who is perhaps the stroke of genius behind a lot of what we think of now and when we talk about the interface taxonomy. So take it away, Mark.
Thanks, Steve. And I've been watching a lot of the presentations today, and they've been really fantastic. And I just want to say, in terms of genius, I don't know if it's an ingenious thing, Steve, but your swimming there at Ontario Place, not only today but every day and for the last couple of years, you really are the front line of clean water. Having a swimmer in the water really puts all the government regulations, gives them meaning and force. And so I just appreciate you and all the swimmers out there who are helping Swim, Drink, Fish keep sewage and toxins and waste out of the water. So thank you very much, and I hope pretty soon it'll be an official beach. Yeah, so I'm an old criminal lawyer who, at one point in my career decided that instead of defending criminals, I thought maybe because I grew up on the Great Lakes and grew up at the end of Lake Ontario, that I'd like to apply some of my skills to keeping pollution out of the lake, prosecuting polluters, we used to say. And it was a group called EBI, Environmental Bureau of Investigation. And like FBI, most of the agents were lawyers because they knew how to put together a good case. And so we said they pollute, we prosecute. And when I would go around and put together these cases, the one thing that was missing was the swimmers, people fishing, people drinking from the water, these human uses. And I knew that, all of our laws were meant to protect humans, but at the same time, once they protected humans, they protected nature and wildlife. Whereas if you put up no swimming, no drinking, and no fishing signs, which I'm sure you've seen everywhere you go, we all see a lot of them. They were put up to protect people in the short term, from toxics, etc. But in the long term, what they did is they normalized pollution and took the attention away from these really toxic areas. And people just thought, well, that's the way it is. I live in a city. You can't go swimming in the water, the river, the lake. That water, the water is only good if it's officially sanctioned somehow, or you don't eat the fish from the Great Lakes because of the Myrics and PCBs and other toxins. And that normalization pushed generations of people away from the lakes. And so when I was doing these prosecutions, the laws required that in order to protect the water, I needed to have someone swimming out there. Then all of a sudden, the Environmental Protection Act, had force. The Ontario Water Resources Act had force. If I found someone fishing and they would tell me that they ate the fish, then the Fisheries Act had real meaningful law. And so as an organization, I realized that the adjective from the Great Lakes Water Quality Agreement in the late 60s, which first put out swimmable, drinkable, fishable water as the gold standard for protecting our water, that these were adjectives, and I wanted verbs. So swim, drink, fish. These are take action verbs. They're very active oriented, and we got rid of the adjective and turned them into verbs, and we call our organization Swim, Drink, Fish. And so it's pretty clear, that our work really revolves around those actions and activities, and that those who are doing them are truly on the front line of environmental protection. And that's what we want. We care about water. Because I care about water, I care about our work. You saw Isabel and Maddie today helping do some sampling there of bacteria at the Ontario Place Beach. We share that data. We like to think we're at the confluence of people, humans, and technology. I think you've talked about that, the vector there. But we get out there, we connect at the water's edge, and we collect data and share it. And we're sharing it in better ways today because of technology. We can now share our data and not have to put it in boxes and do op-eds and papers. We can just share it through open access, and anybody can see it and use it and benefit from it. So that's that's how we think of our work. But there's no better way to see our work in action, or to see it really emblematic, to see it in real action, and than to see you and the swimmers that you regularly swim with out there in Lake Ontario, in an area that Toronto thought was lost years ago. I don't know what else to say today. I don't have the slides, and I'm still thinking about those smart toilets and all the great information that we could get from those toilets about what probably in a city like Toronto with CSOs, combined sewer overflows, that means when it rains, the sewers and the stormwater go into one and all get discharged. It'd be interesting to know what's in the toilets before they're discharged into the lake someday. So that'll be great. We'll be able to use that information. But yeah, I just, I don't know what else to say. Anybody have any questions for me? I can, one thing that we do, if you look at www.theswimguide.org, it's a free, it's an app as well on Google and Apple, and it's a website. And there are over 8,000 beaches, publicly accessible beaches there, all across North America. In Mexico, there are 11 countries now, I think we have beaches in, where we update the water quality data. So We're constantly working with public health and affiliates and collaborators and NGOs to get the water quality data on a regular basis and share it into SwimGuide. So when you go onto SwimGuide, and go ahead if you want, I'm going to put it in www.theswimguide. There it is. I put it in the chat. And if you go there, find your beach, find your water quality place wherever you live. You can be in San Francisco or New York, Miami, and find your beach. And then you can go to that beach and look at the water quality data, how often the water is being sampled. Here in Toronto, it's every day for the 11 beaches at the City of Toronto. A lot of places it can be weekly or monthly. We have that data then uploaded to that beach, and then there's a graph there as well, which shows you how many times it was monitored and how well the water quality was. So it'll tell you if it's green, it means it's it's a go for swimming. If it's red, don't go in the water. If it's yellow, it means special status. Read a little bit more on the page about why. Maybe there's a shark swimming around. Or it's gray, and that means there's no data. So that was really one of our great examples of people, water, and technology, and bringing it together in a meaningful way to answer people's number one question they ask me, which is, can I swim in that water? And that's the number one question we get, believe it or not, as an environmental group. Where can I go swimming? And so SwimGuide was made to do that, but it requires thousands of people monitoring daily, weekly, but instead of putting that data into a box or doing a report once a year, it's uploaded onto SwimGuide within 24 hours so that it can be shared with the public and answer a simple question.
Excellent. That was a fantastic talk. That was really, really good. And I like the way that you're looking at it from human needs, because I guess the lake has no rights, and the animals and wildlife have no rights, and the vegetation has no rights. But I guess as soon as a human enters the water, it's very, very fascinating. It's super interesting because for me anyway, downtown Toronto has only one beach, Ontario Place Beach. It's the only beach in downtown Toronto. And when you go to the Ontario Place website, it says, is there any place to swim at Ontario Place on their frequently asked questions? And it said swimming is not allowed anywhere at Ontario Place. So it was very interesting because we'd go down there, swim, and then the security guards would tell us not to swim. And so we formed that Facebook group called Swim OP or Swim Op. We call them Swim Ops when we go down there for a swim. OP stands for Ontario Place. And so we'd go down there and swim, and then they'd say, well, we're not allowed to swim. So I said, well, are we allowed to have a boat down here? And they said, oh, okay, yeah, you can have a boat. So then I asked myself, well, what's the minimum viable vessel, the MVV? It reminds me of a time when the restaurants were all closed late at night, and the only place that was open was a drive-through restaurant. And we walked up to the drive-through window, and they would not serve us because we were not a car. And I was saying, well, I've been discriminated against as a cyborg. I've been physically assaulted in restaurants for wearing a seeing aid that helps me see. But this was the first time that I was discriminated against for not being a cyborg. In other words, I didn't have enough metal around me for them to serve me. So I said, well, we were saying there's a dumpster across the road. How much metal would you like us to go get and wrap around our body before you'll serve us? Like, do we need wheels? Should we find some old tires and stick those to the side of the metal to push it through at the drive-through restaurants so that they'll serve us? Because humans are a subspecies, and cyborgs are we used to say people are subhuman. Now we say, well, I'm just a bare human. I'm sub-cyborg. And so the same is true of the lake. I said, how much vessel do I need? Like, I can bring my yacht. If I put a hot tub on my yacht, can I be in the water? If I put a pool on my yacht, can I swim in my pool in my yacht in the no swimming zone? And then I said, well, what's the minimum viable yacht? What if I cut a hole in the bottom of my yacht so it's all lake and the yacht's just a floating frame around me? And then I make a motor system so when I swim forward and swim towards the front of the yacht, it motors the yacht along, and then the yacht's just this machine that goes around to let me swim in the water. That should be okay, right? And then I got a dinghy, a little rowboat, and I cut the bottom of it out so I could swim inside it and push it along. And then
You're a great client, Steve, by the way, after all this. You've been thinking about all these things. As a lawyer, I'd be able to really make these arguments for you, either at the Wendy's window or at Ontario Place.
It's all the same, how
Yeah.
we bare humans. It's funny, I've been a cyborg since I was 12 years old, and suddenly now I'm seeing the other end of that two-edged sword, which is is the right to be a non-cyborg, the right to enter the water. Like, you can't go to Toronto Island, they say. You're not allowed to swim there. You have to be in a vessel. So non-cyborgs are not allowed to the island. And that's when I also got a paddleboard. I said, oh, a paddleboard's great because legally it's a vessel. Although it's not a vessel, it's convex hull. There's no way to go inside it. It's not a vessel. It's totally convex, but legally they call it a vessel so they can regulate it, and which is a good thing. You know, you need to have a life jacket and a rope and a whistle, which is a good safety thing. But it also means that since it's a vessel, it can go wherever vessels can go. So now I can take my paddleboard anywhere vessels are allowed, and of course you fall off a paddleboard. It's part of paddling, and you get back on and you fall off and swim back to it. So then you're swimming in a no swimming zone when you're on a paddleboard. And so as long as you got a paddleboard attached to you, you're sort of allowed to swim because that makes you a cyborg. Even if you're not on the paddleboard, merely having a paddleboard attached to you with a tether turns you into a cyborg in some sense legally. And so
Yeah.
it's really interesting. With a paddleboard as a tow float, we swim to and from the Toronto Island quite regularly.
Well, there's a new proposal there to turn it into a swimmable beach, which means it'll be monitored and sampled, and you won't be you have to be a cyborg to go swimming out there. But you need, you need to keep swimming out there. I just want to say, like, what a great format you have here as well, Steve. I see Ryan's gone, but I guess this is just on Facebook. I don't know much about these what you're doing in this conference in terms of how you set it up, but really nicely done. Feels really natural. I feel like I'm in the studio with everybody, so really good job. Maybe you guys have done it for so long. It's really good. Yeah.
Yes, it's a real honor to connect with you too. I mean, we've admired your work for so many years. You've done so much for us and for the community. It's fantastic, and we hope we continue our collaboration as we make everything swimmable. You know, like, I think we should regularly have swims to and from the island, safe, of course. We always have a whole bunch of paddleboards together so we're visible. Get about a dozen paddleboards together and just pick a time when there's not too much boat traffic, and we do regular swims and just raise the awareness and get people out in the water and
Yeah.
make the lake swimmable. You know, it's just so beautiful and scenic to be out on the Toronto skyline, and you look
Oh,
at other beautiful cities that have beaches right in
yeah.
the urban center, like San Francisco has stairs going
Yeah.
down into the water every 400 meters right along the busiest, probably the busiest, one of the busiest ports in the world, and it's
Yeah.
got bathing entrances every 400 meters, steps going down into the sea.
Well, I've told you about what happened in Kingston. I mean, that's where I started back in the 90s prosecuting the city of Kingston for a landfill in the inner harbor at Cataraqui. But the city, after they were convicted, and it was a private prosecution, and they were fined, and they cleaned up the landfill. But the community that was born out of that prosecution under the Fisheries Act really carried on to the rest of the waterfront. And the city of Kingston, then we went after their sewage. They had a lot of CSOs, and it was the sewage treatment plant was too small, so they had to expand the pipe to the sewage treatment plant, upgrade it to secondary treatment. Through all of that, they had mass swims. They had shoreline shuffles where artists came out and put art along and really got people into the water. And eventually, the city of Kingston's water was swimmable. They also created what is called real-time monitoring of all their pipes. So if you go to the city of Kingston Public Utility, every pipe is there live, and every one of them has a real-time monitor at the end. So if there's anything being discharged in the water, you can go and see see where and what's being discharged in the volumes. And that is state of the art. And every city should have that. Toronto should have that. Toronto releases their reports once or twice a year. We don't know what's coming out or where. But because of that real-time monitoring, because of the the greater investment in infrastructure and separating the sewers, we had the opportunity, working with the Weston Foundation, to give them $500,000 to build a swimming pier in front of Queens there. They named it after our board member, Gord Downey. He's a singer for the Tragically Hip. He used to live across the street from that area. It was an old coal dock. And he always said that, he'd love one day to be able to swim again in Kingston shoreline. Well, he did pass away before it opened, just about a year. But it's now called the Gord Edgar Downey Pier. It's 20 feet of water at the end of the pier. It's got a big jumping, you can jump off into this incredibly deep, cool, clear water. They also built a walk-in ramp, accessible to anyone. All ages are there. There's a shallow area. There's a beach. There's steps like you talked about in San Francisco. Claude Cormier, the architect from Montreal, who's done some other parks in Toronto, like the Music Park and the Sugar Beach. He did that in Kingston, and it's the most popular place in the city of Kingston. It's changed the whole city's identity. It sees itself as the freshwater capital again, and truly it is, at the end of the Great Lakes where the St. Lawrence starts. So I think the same thing can happen in Toronto. I think that Toronto should be, so proud that it sits on this freshwater, incredible freshwater wilderness, with the rivers running from the Oak Ridges Moraine through the city down into the lake. And all of it is it's a reflection of who we are and our health and wellness. So I want to get it cleaned up. I want to get people in the water. And I definitely want to celebrate you and all the swimmers who are really, Steve Hulford as well. I mean, in the work you did with the real time monitoring around water temperature, that we're able to put onto Swim Guide, and people are using Swim Guide more because of that. It's really helping us get our tools known, and hopefully these will grow into other cities around North America and the world.
That's fantastic. I mean, that swim pier is something really, really wonderful. That is a real stroke of genius. Like I've been saying, we need something like that in Toronto, because right now, actually, you can go out to Ontario Place and there's a break wall, and you can jump off the break wall, and there's actually a high elevated part of the break wall that goes quite high up, but it's a little bit dangerous, I think, because there's metal underneath, and we need something better. And the other thing is, a lot of children jump off the bridges at Ontario Place. There's some bridges that are about 20 or 30 feet above the water, and children constantly jump off those bridges because it's fun and everything. But what we need is something like the Edgar Downey Pier here. And in fact, I wanted to suggest building an educational pier, like creating something that's like a combination between a science center, a university, and a research lab and a water park, where there'd be, for example, a jumping pier that has 1 meter increments. So you could jump from 1 meter, 2 meters, 3 meters, 4, 5, 6, 7, 8, 9, 10, and experience head. We're almost going to call it head games, because it allows you to experience hydraulic head as an educational institution, as a learning experience. And I put that in the, like we have that, if you look in our conference proceedings, we suggest that idea. We show the one that you built in Kingston as our source of inspiration, and then how we would build on that and add to it an educational component, so that it's actually a teach beach, where you learn by experiencing head.
It's wilderness out there. It's so beautiful, and it's right in downtown Toronto, and it's our Rocky Mountains, and we just think it's an old polluted place that no one goes to. And here we have this access to something magical, and something that can truly, be a gateway for anybody who's gone swimming. Knows what it feels like. It's like being in space.
Yeah, it's like a floating in outer space, especially with the VR glasses on while you're swimming. It's just
that's all that curiosity about everything else to learn about water that we need people to learn, because we need to protect it in more smarter ways, more meaningful ways, and not take it for granted. So it's a real portal to a different world, and we think that that's the best way to deal with so many of these environmental issues, whether it's climate, plastics, pharmaceuticals, nuclear waste, whatever it is that's going into drinking water, into fish, our food, our drinking, or just when we recreate in it, all of that. We need to understand better and do a better job of being respectful of this incredible natural wonder right at our doorstep.
Oh yeah, that's absolutely well said. I mean, I hope we can work together. And being out on Ontario Place, it feels like you're in Lake Muskoka or something. It's just so beautiful out by the beach there. It's a rocky. I really do like the beach too, because it's a pebble beach, so you don't have all the grit and grime and sand everywhere. So the water is crystal clear.
Well, that's one thing, Steve, I always do say. Canadians, I don't know if you know, but Canadians they don't really walk into water on beaches as much. Like, we go to Florida and do that every once in a while, and there are some beautiful sandy beaches. But Canadians all love to have a dock that they run to the end of and jump off. And I think for Toronto,
jumping pier.
Jump off. Just like you said, they're going up there at Ontario Place and jumping off. We like to jump. So we need to build something that we could jump into the water. Maybe it helps because it's so cold. I don't know how you walk in there in the middle of the winter. Oh my God. I just want to get in. And
but it was beautiful today, 3.2 degrees Celsius, the water, and it was nice and refreshing.
Yeah. And I also like when you said that the water can't talk. It's so true. I remember you did the swimming in January, and I turned the mic towards the water, and you guys came out and spoke to it. You know, we have to speak for the water. It can't speak for itself, and so we have a real obligation to stand up and represent clean water. And I know you do a good job of that. And really, thanks for featuring some of our work here today.
Yeah, and if water only had a voice, there's a
Yeah.
Greek word that means the voice of water, and that Greek word is hydrolophone, hydrolophonos in Greek.
Oh.
And the word hydrolophone, it's a word that we made up that means voice of water. And what it does is it gives the water a voice. And the feeling that we had is that if we think of the lake as a musical instrument, at the Splash Festival in 2011, we turned the entire Lake Simcoe into a giant musical instrument. And the philosophy was, you know, if you had a Stradivarius violin, would you throw garbage and would you use it to store rotten apple cores and things like that? And so there's a certain respect due to the musical instrument. So we had this voice of water. We see the hydrolophone as a way, perhaps, of giving water a voice. And you can tell by the sound of the hydrolophone when the lake is good. And of course, the best sounding water is from some of the lakes like Lake Temagami up north. And so we're also doing a project to use hydrolophonics to measure the water quality by looking at the sound wave propagation in hydrophones in the water.
You're so creative, and you're so scientific. That's quite a confluence for you. Nice job.
Beautiful. Okay, well, now
Okay.
thank you so much. And now we have Mark Fox, who is a real expert in the world of smart cities. Mark Fox is a genius, an absolute genius when it comes to looking at ontologies of how cities work. So we have, he looks at smart cities and water, and what we want to do is connect with the work that Mark Fox does and in the area of smart cities, and see if we can bring that in and merge and join forces within University of Toronto. My goal here is to bring together University of Toronto, MIT, Stanford, and create kind of a nexus of water, humans, and computing, or water, humans, and technology more generally, and see what we can do to make the world a better place by really looking at the boundaries or borders between these three areas and what happens at these interfaces. So Mark, are you ready to go?
Thank you very much, Steve. Can you hear me?
Yes,
Yep.
I can.
And is it clear? Okay, great. Thank you. And I've been enjoying the discussion in the 15, 20 minutes that I've been sitting here. I was just curious, as when you're talking about levels of entering water, have any of you seen the step wells in India? I mean, just that picture came to mind, Steve, when you were talking about those, different steps, different levels, and jumping up. But the step wells are the inverse. They go down as opposed to up higher to get into water.
Yeah.
Anyway.
I think something like that. It's going to be really fun if we could. I'd love to work together with you, like Mark. I think if you and like if the two Marks, if I could get together with the two Marks here and the three of us, I'm sure we could come up with something really, really awesome to build like a swimming pier in Toronto with kind of like steps going up to different levels and experiencing hydraulic head. Like as an educational framework, we could do research on it. I'm almost envisioning like a university, a combination of a university and a research lab and a theme park and a conference center or something. I don't know. I got some, but anyway, well, let's, I'm loving, just super anticipating what you have to say about this, how you respond to this.
I'm just trying to find which of my screens are screen 1, 2, and 3. So bear with me for a moment. I'm going to start my.
Yeah, no problem. Take your time.
Let's see. Perfect. I think I actually did the right one. So can you see the entire screen?
Yes, we can. Urban Data Center, Mark Fox.
Okay, great. Okay, so a bit of background. My background is in artificial intelligence. from long ago. The areas that I have worked in from a theory point of view have been combination of knowledge representation and in reasoning with constraints. And I've spent a lot of time dealing with large organizations and reasoning problems, planning, scheduling, et cetera, within those organizations over the years. And more recently, where given that I've been around long enough, more recent means over the last decade, I focused my attention on cities and the reasoning problems that cities face and the knowledge representation problems that cities face. And even more recently, as it relates to water, we've had a project for the last year and a half with the City of Toronto Water Department, in which we are using knowledge representation, and the current term used to refer to knowledge representation is ontologies or applied ontologies. That is, how can we create representations of the things, the assets that exist within the Toronto water system, which covers both water and sanitation, and covers both what they refer to as a horizontal network, which is distribution, both going out and coming in, and also the vertical assets, which refer to the actual processing, whether it's generating potable water or it's processing the sewage before it goes into Lake Ontario. But I also work in a number of other areas with respect to data and ontologies and standards, working in the area of transportation, working in the area of social services and impact modeling of social services. And it goes on and on and on, the different areas that I've done work in. All of this has culminated in current efforts underway by me and others of taking the work we've done and developing international standards. So I'm involved with the ISO, the International Standards Organization / IEC, the International Electrotechnical Committee, Joint Technical Committee, and in particular with what's called Working Group 11, which focuses on smart cities. So my participation in that working group is in the development of standards for the representation of city data, city knowledge, et cetera. And we have a number of standards that are making its way through the standards development process, and already have one of those standards that have come out in the area of indicators and measuring performance of cities. What I'm going to present within the next, I'd like to get through it in 15 minutes so that we have sufficient time for conversation. But what I'm going to present is my most recent initiative, which is the creation of the Urban Data Center in school cities at the University of Toronto. The school cities, just from a background point of view, is a multidisciplinary, transdisciplinary unit within the city, sorry, the school within the University of Toronto, which brings together the various divisions, departments, and faculty across the university. So it's not centered in one division or department of the university, but brings everybody from the social sciences, performing arts, engineering, sciences, archaeology, et cetera, together to work on problems that cities face. One of the things that I've always wanted to do within the school is to create a center focusing on urban data. And so the mission of the Urban Data Center is both to expand the opportunities presented by data in addressing city problems or just city operations, and also address the challenges inherent in data. So it's both an applied view of urban problem solving, but it also is more theoretical in trying to address the issues in using data and creating data, et cetera. I'm going to give a quick tour of the different work streams, some of which were underway and some have yet to start in the Urban Data Center. one being the Urban Data Repository, second being urban data partnerships, third being trusted urban data governance models, fourth being national network of urban data curators, the fifth being standards for the representation of urban data, six, the tools for management of urban data, and seven, the tools for analysis and interpretation of urban data. So I'm going to take you through each of these. Usually there's one to two or three slides on each. So we're not going to go into any depth on any one of them, but just to give you an idea of what our concerns are. So the work stream one is the Urban Data Repository. We want to provide a repository of Canadian urban data that is openly available for use by anybody across Canada, across the world. And so it's going to be sourced from both authoritative and non-authoritative sources, spanning all urban dimensions, whether it's physical infrastructure, social infrastructure, public health infrastructure, etc., and supports research in urban data science such as curation, validity, authenticity, cleaning, trust, relevance, fusion, access, ownership, and privacy. All of these are fair game for what we're trying to do in the Urban Data Repository. The repository is going to have a catalog that provides access to open data sets that will be stored in the repository in their original format. Closed data sets not stored, that will not be stored in the repository, but accessible under separate agreement. And also web service access to data services, including real-time feeds, etc. Now, critical to the building of this repository is the catalog itself. And so the catalog is really where all the action is, because it will be a very rich representation of the three categories of data sets and data services that not only includes information about the provider, when it was created, usage license, the data model, but also information about the quality, completeness, validity, authenticity of the data, and also how the data is being used by others and what types of outcomes they've generated with that data. So this is going to be a very rich representation of the data sets that are either open or closed or accessible via web services. Now, all data sets are going to be stored in their original format. That is, if they are provided to us, we will store them in the original format. We're currently using CCAN as the platform for storing that, but all the data sets are going to be integrated into a single knowledge graph. Right now, we're using Graph Data DB, but the data that's openly available here will go through a transformation process where it goes from what are typically table-based, relational formats into a graph representation with the attachment of metadata, mapping onto ontology-based standards so that we can integrate the data by having the same classes and attributes being used to represent the data, and then merging all that data into a single knowledge graph. So that's the ultimate goal of what we're trying to do, is create highly integrated data sets dealing with the issue of integration that makes using data today very difficult around the world. The second work stream is in the area of urban data partnerships. The goal is to enable the use of data for policy. Well, the goal is basically develop partnerships with a variety of organizations out there by first developing a roadmap that explores the types of data that might be made available, formalize research partnerships with stakeholders, streamline access to data, etc. The idea is to start identifying sources and creating contracts with them that allows for their data to be deposited in the Urban Data Repository. So far, we've already begun relationships in the health data area with the Public Health Agency of Canada, municipal data with Federation of Canadian Municipalities and StatsCan, City of Toronto Digital Information Plan, from a governance point of view, Innovate Canada, and from a standards point of view with the ISO/IEC group and the World Wide Web Consortium. Third work stream is the development of a trusted urban data governance model to explore models of legal, political, sociological, practical aspects. Trusted data governance process, as I said, is to ensure the ethical and responsible collection, processing, use of data. There are two types of governance that we're concerned with. One is what can we access, which involves the use of issues of privacy and rights to use, etc. But secondly, what we can use it for, which involves acceptable use of data regardless of source. And there's a lot of concern in governance on who can access it. There is not as much concern with what are you going to use it for, what are you going to do with it, especially if you start aggregating and re-identifying data due to the fact that you're bringing data together from multiple sources. And as part of the urban governance, we are going to be addressing the issue of who, what do we trust? Do we trust the organizations that are providing the data? Do we trust the ownership of the data? Do we trust that it doesn't contain any personal information? Its authenticity, do we trust? Its quality and the ethical and legal acquisition and use, do we trust that also? One of the key things that we're going to be pursuing is the issue of the approach of taking a life cycle perspective to the whole issue of trust in any type of governance framework, where we look at the issue of data trust and governance as being a you want me to stop, Steve? So put yourself on mute because we can hear you.
Over here.
No, everything is good. Everything's good. We're just looking at the slides here and
Okay.
and trying
Just put
to get the
yourself
best.
on mute. Just put yourself on mute.
Put me back on. Let's put me back on mute here.
Yeah. Anyway, the view that we have on governance is any governance model is fallible, okay? And that governance should be viewed from a life cycle perspective, from the deposition of the data into the repository to different stages of making it available in the catalog, to downloading it, to using it, etc. We have to look at the life cycle. No, I don't have any. Oh, I see that. Yeah, it's coming through there. I don't even have that. Okay. Oh, I got lots of windows open. Hang on, but not on that screen. That's interesting. There's computer science appearing there, and I don't see it anywhere else. Oh, you know what? It's the application that we're using is keeping two rectangles from the very first slide. Well, let's do the share again and see what happens. Anyway, I think we can select the window, screen 3. Okay, allow. Okay, you're not seeing it appear there. Do you see? I don't see it any longer, do you? Yeah, so it's the same thing I'm showing, but I just restarted sharing, and it appears that the sharing system retains certain information from one slide to the next, because those two things were coming off of the first slide. Anyway, we're looking at the issue of governance from a life cycle perspective. Different organizations have said, do self-certification. I mean, there's Sidewalk Labs approach, et cetera. We think all of those are problematic and think we need a different approach. The National Urban Data Network is a network of data curators that will be located in libraries and universities across Canada. And their role is to identify sources of urban data, secure rights to the data, annotate the data with the meta information for the catalog, and deposit the data into the data repository. The next work stream is standards for the representation of urban data. The focus here is to provide precise, unambiguous representation of city data, enabling its integration across city services, both within the city and external stakeholders, enables cities to share data basically. And we've have extensive amount of work that's been underway in that area. The ISO IEC 5087 series of standards has multiple levels of standards. 5087-1 focuses on foundation level concepts such as time, location, activity, resources, etc. Level 2 is a citywide set of concepts and attributes, properties, such as household services, residents, etc., that are shared across the city. And level 3 through N are service-specific standards for city data that are specific to the service. So transportation planning is 5087-3, and it focuses on vehicles, on transportation networks, on trips, and etc. 5087-4, which we're currently starting the standards process, focuses on public health emergencies. And wouldn't it be great if 5087-5 focuses on water? So I'm going to skip over that. And the next work stream is tools for the management of urban data. This is data science research into data validity, determining the degree to which data that is provided is actually correct or true. Research into semantic integration. How do we take data from multiple sources and integrate it? The standards provide us a foot up, but mapping data from diverse sets of data models into a standard is itself a major challenge. Research into privacy and ownership. What role do we use role-based access, organization-based access? How do we deal with source-based governance like OCAP, which is the First Nations Information Governance Center ownership, control, access, and possession principles? Support data. This work stream will focus on data quality, whether it be measurement quality of sensors, sampling quality, classification quality, etc. And also focus on temporal management. What do we do? How do we represent and deal with data that is continuously changing over time? Well, I'll leave it at that. Then I believe the last work stream is focusing on tools to support the analysis and interpretation of urban data. This is not a better machine learning algorithm. What its focus is on tools such as experiment management, allowing for the specification of goals, objectives, metrics, data sets, and analysis process, specification of analysis process or pipeline, where you take multiple operations and apply it to data, and then applying data analysis modules to it, whether it be statistics, machine learning, and also visualization. But again, most of our work here will be in the utilization of existing tools as opposed to coming up necessarily with a better visualization. So that's a quick introduction to the Urban Data Center, and I'm happy to take any questions.
Yeah, that was an. Oh, just come back here. Yeah, that was a fantastic talk. You know, I'm really excited about that idea of having water in there. I'm just looking on the looking at the questions. I don't see any questions yet on the. But again, we'll keep this discussion going on the. If you come back to the WaterHCI website or Facebook page, we'll keep the discussion and questions going. But it's a fascinating idea to looking at the whole state of urban planning and like bringing water into this is excellent. And I also love the ideas of ontologies. Like, I think there's a lot to be done with ontologies. There's a lot to be done with knowledge graphs. There's quite a bit that could be done in terms of the interplay between humans, water, and technology in terms of graph, in terms of an ontological framework. And maybe we can work together on that. You know, Mark, you and also Mark Matson, the two Marks, and I and Ryan here. Ryan will be up speaking next on the science of hydraulophones, science of absement, which is the area under the time distance curve, and also talking about hydraulophones. Ryan founded Transpod, raised $65 million, and was won the Innovation of the Year award. So I'm very proud to have. It feels absolutely wonderful to have such a genius like Ryan. I often think of him as a modern day Leonardo da Vinci, kind of an engineer. I would say an engineer, a scientist, a mathematician, and a musician and a plumber all in one. So yeah, Ryan, if you're ready to go, you want to start a little early.
Okay, wonderful, and thank you, Steve. And I'd like to applaud everyone here on a lot of the the things that really matter to people in an urban environment, and how we can live our lives, smart design, and so on. So we really have to design our world intelligently, and also it was really a pleasure to be a collaborator with Steve and many others who really have this multidisciplinary view, and I think coming from all of our work together, it's a wonderful experience, and lots of research ongoing that really I think one thing that Steve and I really share is a focus on both the past and the future. Some people, I've been noticing some people look at the middle, like just now, but you have to be really thinking of what came before and really looking forward to what comes next. And I think, and Steve is really an inspiration on that. And also, this whole event is quite key for how we combine research and making lives that human interaction that really matters to all of us. So I'm going to be talking about a few things. So I'm going to be talking about massive infrastructure projects, and I'm also going to be talking about new research. I'm going to be talking about kind of art and science and how they go together, and kind of a framework to put it together. And then we'll end with some fun with some music, and I'll show a few things that we've done with the hydraulophone. So okay, just a little bit about what I'm doing right now. So at the moment, I'm leading 24 universities and companies around the world in 8 countries, and we're designing aerospace vehicles and also transportation infrastructure. And it's really many different kind of products and designs that all go together, and even some medical applications too. And so it's very there are many parts of the projects. There's some of these projects that involve architecture, urban design, but also really combining very new research. And so with all of those projects, something that's really relevant to all of us here today, I want to show you how with many of these big projects, you have to understand a kind of fluidity between human and machine, and I'll talk about that today. And so this, what that really means, and so how this fluidity is really needed in the design of high-speed transportation vehicles, how it's really needed with both music and physics, and so the arts and science, and how we really need to understand that interaction between humans and machines. And so I'm going to show you with with the transportation example. So let us go to that first big example, and then I will be showing how that relates to musical instruments. So we'll show some fun musical instrument things. So first, I'm going to share the screen. Okay, so can people see the screen right now? Hopefully, yes. So if you can see the screen right now, I'm not sure if it's coming through on the broadcast yet. Is it? Maybe someone can say whether you're seeing it. Okay, excellent. Okay, excellent. Thank you. Thank you, Steve. Okay, so first I'd like to tell you about Transpod. So we're designing an aerospace vehicle and transportation system to carry people, so passengers between cities at over 1,000 kilometers per hour. And so this is a very big project. It involves design of basically the Transpod vehicle, which is like a jet without the wings, and it operates like a train. And it goes through a protected guideway. So this is a new type of tube transportation that was conceptualized, I mean, the basic concept from over 100 years ago. It's been iterated, different conceptual designs, but now we've solved some problems with some of those previous designs, and now are working with several governments in North America, Europe, and Asia on implementation of this transportation system. So we've signed a memorandum of understanding with the Alberta government for a few $100 million first phase. And so this is part of a big process to get this kind of system tested. I'm also working with the European Union, where I have kind of an appointment as chair of a committee working on the regulation of this kind of technology. And we're aiming to set up the same kind of thing in Canada. We're also working with the federal government in the US about this. And so it really all comes down to the core design and fundamental physics and getting the physics right. And actually, what you see here, there are two things. One is that the vehicle you see here, we're actually going to be doing a big product launch, a big unveiling of the new vehicle technology, which is actually not exactly what you're seeing here. So there's a brand new thing that we've been working on for actually a few years now, and it's going to be announced to the public. Very excited about that. So that's coming in a few months from now, yeah, it's quite exciting. So this kind of this public-facing version that's a little bit older. It's quite a few years old. This is the same kind of fuselage. So it's the Transpod vehicle built like an aircraft, and it's a bit bigger than it might appear here because it's actually the size of a small jet, where it's able to fit in one configuration for seating 27 passengers, but we can actually have it up to 45. And so it's electrically powered and propelled by moving magnetic fields with these linear motors. And we have some pretty special technology for the energy management and propulsion and guidance and control. And so you have the guideway, which can be up above the ground or at ground level or underground. And so this Transpod line is what we call it. And so that can have a guideway for both directions. So these tubes that actually manage the aerodynamics and have lower friction, just because we're removing some of the air pressure. And so we're working with the design of this kind of system in quite a few cities. The most interesting one recently was in Thailand. So it's amazing the amount of infrastructure that's being built there right now in Southeast Europe sorry, South Asia. And so in Thailand, that was a federal project where we're doing a first study. for a transport line there. But a few of the other cities in Europe and North America, where we're working at the government levels, and then working with quite a few partners on the initial development. So it's very a lot of exchange of many of these aerodynamics and civil engineering and propulsion and many other things. And so it's a type of tube transportation that you could say. And there were previous kinds like ET3, there was Swiss Metro, there was Hyperloop, but now we have a new kind called Transpod, a new kind of tube transportation, and solve some problems with those previous ones. And so, and many different interesting technologies in guidance and control, and in also looking at the aerodynamics, vortex shedding, and actually this is looking at the skyway from the side. So those two tubes looking down the direction of those two tubes, if there's a hurricane force wind, because of course safety is a key thing there, and so the safe structural design and that vortex shedding, the fluidity, it really brings us back to there's a couple of really good examples of how fluid and flow is really key. And actually, when we've been working with, so Steve and I on the hydrolophone project too, that vortex shedding and the fluid flow, really smooth flow is really key to analyze, and when you can make sound from that actually. So you're going to see that in a moment. And even with vibrations of these structures and so on, and so it's really neat when you actually have a lot of these kinds of structures. You really have to think about all of the dynamic effects, and so this is kind of one of the stations that we've been working on, where the transport vehicle pulls up and does sort of a docking procedure, and passengers disembark and once unload on different sides, and so it's very much like a train station. And so just a really quick view of one of the test track. We have the construction permit approved here and have begun early phase of construction. This is actually for France. This is a smaller test track, like a reduced scale test track. And so the sort of bigger, better one is going to be in Alberta. So that's why we've signed the agreement with the Alberta government for the sort of more full scale testing, unlike this one. And so that's going to be between Edmonton and Calgary, and part of a future transportation line. And so there's all these different stages of kind of construction and testing and working with regulators on that. And so it's really interesting. Maybe I'll just showing different eye candy here on some of the some of these different. Oh, maybe I'll bring that up after. But anyway, I'll show some of the machine shop work that we're doing. That's in another video. So really, I think it's quite interesting. I'll just stop sharing for just a sec, and it's really interesting how all of that design, you really have to get it right. And similarly to how we've been designing those musical instruments and the hydraulophones, it really has to do with a very very reliable and smooth connection between humans and computers and machines. Because for me, from my view, when you're a musician on a stage performing some music, even a small fraction of a second, if something doesn't work on your instrument, it's no good. And same with a very high-speed vehicle. If even for a tiny fraction of a second, the control systems crash or stop working, then that could spell disaster. And so that's why with some of these systems where human lives are in the balance, you have to be inspired by some of the same musical know-how and design techniques in the very fluid interfaces. And that's exactly what we'll show with the hydraulophone, the fluid interaction that is really key. But in the case of really life safety, life critical systems, what we're doing is many layers of backups and fault tolerant systems to make it work. So the fluidity aspect for high-speed vehicles, well, we have to look at the aerodynamics. We're working with supersonic shock waves, and so we have two aerodynamics teams that are working on all of that. So one of them is at a university in France, and one of them is over here, and so all of the vortex shedding from the vehicle and different things like that. Another thing is the really fast control and smooth control, and so part of the patents and everything is on really smooth control. To, even though you have infrastructure, basically, when you're going that speed, driving on a road is easy. A car is very slow, and so if the road goes up and down just a tiny bit, that's fine. But at that speed, it's a major issue, and so you have to have all of these systems that realign at very fast speed to give the passengers a comfortable ride. So it's all about really fine, smooth, fluid control and fluid sensing. And so all of this is full of optical sensors, and it's full of sensors all over, and really fluid control. So, it comes back to, just as when you are designing a musical instrument, where the musical instrument has to be very intimately linked with the human. There has to be a very intimate link between your fingers, or if you're blowing on a wind instrument, what your mouth is doing, and what sound results. And so you can't. So that's why some of these failed instruments actually have some issues. Some of these cheap keyboards that you can buy, or and then on the other side, back to the theremin kind of idea, where you can't tell what you're doing. So you wave your hand, that instrument where you wave your hand and you make ooh. So that instrument is very fluid in a way, but it doesn't have the feedback to the person. And so with the high-speed transportation projects, that's very key. And so we're really looking with not only the mechanics of it, but the environmental aspects too. And so you really have to look at waters and streams and forests and ecological effects. So even one of the routes that we're looking at in Europe, where they actually already have protesters that were protesting a previous train proposal because of the noise pollution, but now with what we're doing, it's more contained and acoustically isolated. So this kind of solutions like that are helpful, but we really have to pay attention to all the ecological effects, even of the construction, and also the long-term effects, and really get the design right with plant ecology, animal ecology and behavior, edge effects around forests, and edge effects at rivers. And so you're using some of the latest research on edge effects and how it affects animal behavior to really design this a smart way. And so, but the whole idea of an interface, a human-machine interface, it surrounds you. So it's really interesting with a vehicle that is your protective surrounding. I mean, you can be in a car and it protects you from. It has some crash protection, some airbags and so on, energy absorption. And so this transport vehicle is kind of like that clothing, that cyborg clothing around you, that is part of that human-machine interface. And so the funny thing is with transport, since we have a reduced pressure outside of the vehicle and inside this tube that it goes in, The tube itself is sort of inverse clothing. It's clothing that's inside out, because it has to protect so you have the environment for the passengers and the environment of the outside world, and you have high pressure in here and you have high pressure pushing in there. So it's the clothing inverted. So you have these different layers between the human and environment and another environment and another environment. And so just as we are about to get into more the interfaces and how, really interesting musical instruments and things, I'd like to share with you. Well, first, why don't I share with you one example of um, some musical instruments, and just to get your mind going on how that works. So this is one example of that, and so I think I'm sharing the sound of this. And so this is a hydraulophone. And so what we're hearing here is the sound of the water inside that instrument as the human fingers are really carefully moving over the water flow. And so this is an instrument that Steve Mann and I and Chris Amony and several other people were working on. And we've had many different types of hydraulophones. So you hear it here, just that really fluid interaction. So if there's time, what I'll do is I will keep on playing more of the hydraulophone, and so I just hope everyone can still hear. So that instrument is really interesting because in how you really have fine control over with your finger on the water, and you really feel that water flow going past you. So it's really amazing to have. It's really visceral experience because it's kind of like swimming. It's like mini swimming. So you've jumped into the pool with your fingers. Now you can actually jump into the full pool with a hydraulophone. And so that's no problem too. And we actually had a concert in Denmark where we did this underwater concert. So we had half the audience sitting in chairs, as a normal music concert audience. Then we had the other half of the audience with snorkels, and they're underwater to hear the sound. And so that was really interesting a concert that we did a few years ago. And it was a place called the Vand Kulturhuset. That was the place. That's Danish for water culture house. And so it's amazing how you can really mix the arts and water, and it's fun experiences like that, because it's really kind of this trying to do this high arts kind of experimental music at the same time as with hydraulophone. I mean, it's part of it is to make it simple too. So if you want to play simple recognizable melodies, then you can play so the different, you can play a scale with the different water jets, or you can rest many of your fingers at the same time and really fluidly move around. So I'll kind of I'll show another example in a moment, but really I want to have like a sort of an intellectual framework for how that fits together. And so let's just look at this, because it really affects how we think about humans and machines in general. And so this is part of some larger research that is really on how we can mediate between the outside world and the human too. And so that same kind of fluid experience. And so some of this is related actually to some of Steve's previous work on humanistic intelligence and how you can have the senses, human senses and machine senses, and then how you can affect the outside world with both, and they interplay. And so so for me, that interesting research was really looking at, so I did some quite interesting things with hearing assistance and seeing assistance that opened up a new multidimensional mathematical framework on sort of smart sensing kind of methodology, and quite a few interesting signal processing and new technologies that can be used for aerospace and high-speed transportation. They can be used for cameras and even assistive devices for humans to help people sense the world around them better. And coming from HDR photography, but working with welding and so on. And so some of these algorithms, I'll I'll just skip through some of this, but it was pretty interesting new algorithms, and it really comes down to even the sensing of sensing itself. And so that was kind of a new thing with valence flux. That was a new kind of creation out of this work, and so the sensing the capacity to sense itself. And so all of this really, and so this was we did the first ever bio valence flux, biovalometrics, and for control panels and so on. But really, how it really is opening up how we can relate machines to humans. And for me, it's with you have a high-speed vehicle or whether you have a musical instrument, you really want to design it in a way that that works super seamlessly, and you can't spare any second of uncertainty with a vehicle where human lives are at stake. And the same thing, it leads to all these amazing stories where we did these concerts with these music concerts with kind of pretty interesting technology, where when everybody's watching, you can't have a frame drop, you can't have anything cut out for a moment, because you just need this really intimate connection, fluid and intimate connection between the person, the musician, and the sound and the experience. And so that it's almost like an experience for the audience, but it also has to be an experience for you, the person. And that's really how we really have to design human machine interfaces to make it really really work, whether you're doing seeing aids, hearing aids, and how it all fits together in what I was calling this sense space. So so it's really kind of an intellectual framework for how we conceptualize all this stuff. And so same with vehicles and instruments. Now let me just close out and we can go to questions. But in the season that we're in, it would be interesting to actually here's actually a piece of music on hydraulophone that was it's quite seasonal right now in the Christmas season. So I hope, let me just stop sharing again because I want to share with sound again so you can hear that. And I want to share this piece. And so hopefully you can see and hear the screen here. And by the way, I don't know if the previous one was coming through, and I'll just and so if you didn't hear this one, this was the hydraulophone where we're hearing this really fluid and continuous sound. And then let's play this one. So this is actually
so we're all rolling, ready?
An immersive kind of hydraulophone.
Speed.
And so there are two hydraulophones being played here. right. So thank you very much, and that is a little look at how aerodynamics and fluids and human-computer interaction, human-machine interaction, and musical instruments really work together. And so the water really means a lot, both for us as people, water and fluids, fluid flow. It's really important for life safety considerations and really how machines interact with their environment. So thank you.
Wonderful. That was wonderful. That was a great talk. Really, really inspiring to see how we can think more generally with the transpod. It gives us the idea that we can broaden this interface taxonomy to think about. Okay, we have a human. When we have today at the beach, we had these smart eyeglasses on when we were going swimming in the ice water. So we had the human inside the technology, inside the water. But now we can talk about the human inside the clothing, inside the transpod container, inside the pipe, inside the earth, maybe under the ocean. So you got these layers of interface taxonomy. And I really do think, like if Ryan, if you and I get together with Mark Fox and Mark Matson, I think we'll be able to build out this ontology in a very profound way as taking a leadership role in this field of research. And we also have Tomoko Yonzawa from Japan and other really great scholars joining us. Derek Lamb will be joining us. And Derek's going to talk about the underwater sequential wave imprinting machine. So traditionally swims, like in the 1970s, we'd put our swim on a little vessel and slide it back and forth on the surface of the water to interact with sound waves in water through marine radar. But and then swim motors would be, ways of putting swims on motors that only really work in air because the swims are like a giant fin that slows the motor down when it's in water. And what Derek is experimenting with is putting LEDs, just individual, like a single LED on the shaft of a motor, and then using it as a form of underwater analog optical communication, because the purpose of the swim is very real time. Like if you look at how swims work, it allows you to interact, human water computer interaction using analog computers originally in the 60s. WaterHCI in the 1960s and 70s was instantaneous, like there was zero lag. Everything moves at the speed of light. And so it provides this very fluid form of interaction that we've come to expect. And so we're often disappointed at modern technologies. I always feel we're kind of like an Amish community that can't stand the delay and sluggishness of modern technology. And you see, I like computers that are quick like they were in the 60s, not computers that are slow like they are today. And so what Derek has done is, it was this LED on the swim. Now we have this almost infinite bandwidth optical communication to the swim that's above the surface of the water or in an augmented reality headset. So it allows us to see the tilting of fields and motors and pumps and water-based interaction. So that will be really good. So we'll have like maybe a 3-minute break because I think we're running slightly behind schedule. So just to get back on schedule, we'll shorten the break to about 3 minutes, which should be enough time to pee. If the toilet talk didn't make you need to pee, certainly the hydraulophone performance will. You'll never have kidney stones if you listen to hydraulophone music because it'll keep things moving. But anyway, on that happy note, we'll take like a 3-minute pee break. And then once we've dealt with the liquids that are inside us, we'll then come back and continue with Derek at approximately just a couple of minutes after 5, like let's say 5:03 p.m. here Eastern or 2:03 p.m. Pacific. Hello. Okay, so we've had a nice little intermission, and I think ready for Derek.
Ready for you.
Okay.
All right. Thanks, Steve, for the excellent introduction. And yes, indeed, the talk that I'll be giving today will be focused on motor and MoValence and its application for underwater optical communication, which is a rather fascinating problem with the original conception of MoValence, which those who are familiar with swim would know had the linear, the bar basically that would show the LEDs and the waveform imprinted in space perpendicular to the direction of motion. Quite a problem when moving through water, 1,000 times denser than air. So I'll be showing how we can use a different perpendicularity to show waveforms of motors in water. Okay, let's throw this up. Okay, so to begin, I'll just give an introduction to the MoValence methodology and its applications. Traditionally, we look at machine pattern control and load analysis through MoValence. And then I'll be giving the contribution here. It's a swim compression for drag sensitive applications. As Steve alluded to, with a single LED swim, we use intensity encoded analog communication. And then we have a software mediated streaming swim decompression. Okay, so MoValence is the visualization essentially of electric machines. And as Steve said, the real-time nature of this, the speed of light, responsiveness of swim is especially crucial in MoValence because the way, and I'll explain this as the presentation goes on, the way that the wave is imprinted is and responds to phase changes is at the speed of a motor. So if the motor is running at 10,000 RPM, the swim, which would be resolving things in degrees of that, would need to run thousands of times faster. So the motors that we see and use every day are largely opaque. They have internal electromagnetic fields. These are invisible. And what we had proposed earlier last year for active motors, and in Pete Scorbataco's work several years ago in designing this for passive machines as well, and who laid the foundation and created the concept of motor swim, is to attach these swims to an electric machine body. And so this is our class, as we know, of visualizing stationary quantities in space that is carried by some known frequency. In this case, this is our motor operating speed. Usually this is done by heterodyning the signal to baseband using the input frequency or chirp as a reference signal. And of course, this is often displayed on a linear array of LEDs, akin to like a dot bar voltmeter. And in the case of swim, the shaft is fixed, basically where all the permanent magnets in a PMSM sit. But the output display, all the batteries, all the electronics are actually mounted to the body of the machine, which is shown here in blue, and it rotates with the motor. So there are two, I guess, broad categories of motor swim. The first one is the passive machine. This is powered mechanically. So what we get from a swim that is attached to the voltage, or across two coils of this, are the back EMF and, in essence, the angular profile of magnetic flux linkage, and we get that from Faraday's law. Now, what you can get out of this is a very interesting machine pattern analysis. The stationary quantity in this case is actually the internal magnetic field of the motor, the permanent magnets in this case. And so every revolution, it sweeps out the exact same magnetic profile under the same load conditions. So we have exact overlap of wave crests, and that's really the underlying stationary principle. What you see here in this animation is actually us modulating speed. And due to just due to Faraday's law, and also the high bandwidth of swims, at higher speeds you don't see any phase contamination, but you do see the true effect of higher voltage amplitudes from higher speeds. And again, since we have an exact correspondence of this visual waveform to the stator position, we can identify asymmetries. We can also see readily the effect of Lenz's law, which is that in one direction we get a one of the two waveforms here, and in the other we actually get the reverse. Yes. Okay, so for active machines, this is work that we did recently, as recently as last year, for powering and measuring the device under test at the same time in the rotating reference frame. In this case, our swim apparatus is constrained to be either battery powered or slip ring powered and radial balanced as well. In the paper that we published to IEEE SVR, we used transconductance amplifiers. We monitored the instantaneous load current using a shunt and then amplified that to display directly on our swims. And then the interesting thing we get with active swims is observations of reactions to control inputs and disturbances. And we can see that in both phase, waveform, distortion, and amplitude. For example, we performed work with machine load analysis using swims and using comparisons between long exposure photographs taken under load and under no load. So here we have one color per phase. We have no load applied on the top and load applied on the bottom, where the phase shift indicated the amount of load due to increased power, the increased power draw. So under no load, we had no mechanical power, and then under load, the voltage and current waveforms aligned and also aligned to the timing of higher torque when sweeping past the rotor magnets. And we were able to calculate the load torque based on this relationship, the electrical angle versus expected torque. Okay, so I guess all that was really introduction to what this will be showing in an underwater swim context. So we know that the prototypical swim, it imprints waveforms along an axis perpendicular in space to motion. And all the swims that we showed previously are spatially linear swims that are built to operate in air. And we have orders of magnitude more drag in water, so we have to shrink the area of the swim by this amount as well. So the water swim, in this case for motors, is a space to intensity perpendicularity. So in fact, we completely skip out on space entirely, and we use a software mediation to invert this mapping in real time. And with that, we're showing fundamental properties of electrical machines. We're using swims to make visible this otherwise hidden rotating magnetic field, and we're augmenting the understanding of our passive and active machines intuitively. And with that, I guess we'll jump over to the demo, unless there are any questions. Okay, let me just get this set up. guess I should actually take the opportunity first to show in real light what we have here. Okay, so just a closer look at this swim prototype. We have our power source and the bulk of our drag, actually. This is the swim, and we have a voltage and current. It might not show very well through the compression, but we have our three-phase inverter, and then we have the completely non-electronic stationary attachment point. So I'll be just hooking that into here. I'm just starting the script up now. Okay, great. Yeah, so this is a post-process script that's running through the webcam on my laptop. And what you see in red, which might be a little hard in this case, but this red dot will show the centroid of the swim as it comes online. Okay, great. And then get it started. Okay, let's see if I can get this aligned properly. Okay, so the inner waveform, what you see kind of on the poles here are the expanded current waveform swims coming out of a single LED, which is the white ring in the middle there. And then on the outer and on the horizontal poles here, you'll see the voltage swim. And these are just the voltage and current waveforms that are mapped to our single LED swims. Now, I'll bring my finger here and then I'll push it onto the body of the motor, and you can see right away, before I actually completely desynchronize it, you'll see that it actually starts to move the waveform over as it matches the load torque by synchronizing with the highest torque points on the motor in the stator. And every time I bring my finger down, you can see the amount that it will shift will be proportional to the amount of friction that I apply on the body. And yeah. There we go. I guess I can stay in the red light for now in case there are any questions about the setup. But yeah, that's our single LED swim for drag sensitive applications.
Very, very nice. That was fantastic. That's really groundbreaking work, because what that really means is it revolutionizes the way that underwater swims can work by simply optical communication. Like, that LED could be embedded right in the shaft, so not only would it be flush with the shaft, it could actually be under the shaft. You could drill in and inset it right into the motor, so it induces zero drag and conveys all the swim information, and have, in a sense, as long of a swim as you wanted, as long as the arms could, in a virtual sense, be as long as they needed to be to make that visible. So that what's really nice about that is we can clearly see the tilting of the magnetic field. So the magnetic field is in there in a certain position, maybe like this, and when you grab it or load it, it tilts the field. You can see that as you apply a load to the shaft by putting your hand against it to make the motor do more work, as you try to slow it down with your fingers, and then the motor has to draw more current to maintain its speed. You can see that field tilts. It's very clearly visible. This is something that should be in every teaching lab. Like everybody should understand this phenomenology. It makes it really, really clear. And we could see even with pumps and motors when there's, depending on the fluid or the characteristics of the fluid or how much head. I mean, it would be really interesting to put this on a pump and play those head games, you know, do this hydraulic head or flow as a hydraulic head as a function of flow, and maybe look at the swims at for different amounts of head. You could look at the swim pattern on the motor and learn a lot about not just the characteristic curve of the motor, but you could even envision maybe like a long exposure photograph with a pump underwater for a certain amount of head, and then move it and increase the head and move it and increase the head, or flow vice versa, and have this thing plot itself a graph of head, of the images as a function of head, let's say. So at 1 foot of head, here's what it looks like. At 2 feet of head, here's what it looks like. At 3 feet of head, here's what it looks like. And literally see the evolution of hydraulic head on an underwater swim. That would actually revolutionize the way the whole water industry goes. So I think this could be really a significant work.
Yeah, I mean, akin to like, you know, turning the turning the valve open, you would have this swim that would actually be turning open as we go along the axis of head or axis of power input. It's a like seriously intuitive, even just for phase. This was originally birthed out of a project I had for improving the phase matching for a sensitive, like a flywheel reaction wheel. So it was highly sensitive to the power output at low speeds. And I didn't have a linear swim on me. And then I realized, oh, actually, this is mostly equivalent, but much more compact. So, yeah.
Cool, excellent. Okay, so now do we have, Tomoko mentioned she may have an issue to deal with. Is she online?
Yes, I'm online.
Oh, okay, good. Are you able to present?
Yes.
Excellent. Okay, well, this is going to be really good. So, yeah, let's roll right into your presentation then.
Okay. So I'd like to show you my presentation. Okay, so here, can you see? Can you see it? Okay. I'd like to start. Okay, thank you very much. I will start the presentation from now. Okay. So, hello, this is Tomoko Yonezawa in Kansai University. And very thanks to giving me such opportunity to talk to you about my past work. Okay. So, today I will introduce some of past work related to fluid interaction with musical toys. Additionally, not only the past work, I would like to introduce some of my work ongoing. So, as my self-introduction, I'd like to show you some movie of current work. I was from ATR, Advanced Telecommunication Research Institute International, and I will give a talk about musical instrument using water in 1999. It's very old, but my current researches are widely treating 3D sound, virtual reality, and educational agent for application, emotional robot with physical touch in the field of human-agent interaction, and musical emotion. And I have technical course in digital music generation using pure data. So here I'd like to show you my current work about artificial emotional touch of a robot. This research aims at clarifying emotional touch patterns of the robot based on the emotional state and the strength of the data. Sorry, and various touches. This is a typical touch of that. So we examine various touches of changing strokes, stroke length, and cycle duration to vary the emotional expression and found some representative touches to express like this. And today I will talk to you about tangible sound, a musical instrument using flowing water string that is a central region of the Steve's taxonomy. Another topic to talk is interaction with fluid body and mind, including statutory musical instruments and water body expression for artificial presence that are not appeared in the proceedings. I'm sorry. So, tangible sound was presented in ICMC International Computer Music Conference about 20 years ago, but the picture was taken in ATL Open House in 1999. Here is a demo movie.
Tangible sound is a musical instrument with a novel user interface using fluid water. As fluid and sound have common characteristics, fluid water provides us with a performance interface suitable for flowing sound and music. For example, both change shape over time, and neither can be grasped. Water is an essential material in daily life, so an instrument using water can be more friendly and even become an amenity in future life. Although there are many installations and interactive arts using water, refer to water's use practical uses of fluid meaningful musical instruments. For measuring the upper flow, we use the radius of the flow under the faucet by sensing the electrical resistance of water with nichrome wire. The lower flow is also measured by resistance of the lower water. Funnels are prepared as drains, and in each drain we put nichrome wires for sensing water level, which is used to measure the amount of lower flow. The level is raised when the amount exceeds the draining capacity of the funnel.
So, tangible sound was a musical instrument aiming a novel experience with the sense of touch on water that changes its shape over time. And also the music and sound also change its shape, not shape, but change over time. musical output are designed to linked to the water state that is changed by the interaction with the user. So then, mainly, Shishiodoshi and Suikinkutsu, a natural garden instrument in Japan, inspired me to design the tangible sound. Shishiodoshi store water in bamboo joints, and the bamboo rotates so that the water is automatically discharged when it exceeds a certain weight, and when it returns after that, the bamboo should hit the floating part and make a beautiful sound like this. And suikinkutsu is like an earthenware pot that makes a beautiful resonant sound of the water drop pouring down from the top. The sound is somehow metallic and mystical. Both objects are beautiful objects that decorate Japanese gardens with soundscapes. An important characteristic of sound and music is just change over time, like other fluid. Water has some same characteristic. Furthermore, the tactile perception of water is similar, but they have uncontrollable factors and bring natural and attractive feeling. Link between them also provides a strong impression and intuitive feeling of that natural feeling, including human control, have some uncertain factor anyway. So here is the detail of the system. Water flow from upper tank to the lower tank is controlled by the faucet. So the amount of the water flow changes the diameter of the water stream, and to sense the user's input on the water, uh, we use several sensors with two Nikon wires. So, such as the water diameter can be sensed by two Nikon wires set like this, and drains. The, the depth of the water is detected by two Nikon wire in parallel. So not only placing the sensors, we should detect the user's input on the water flow. So, such as scattered water drops are sensed in sub-drains because we have multiple drains, not only main drain. So it can be detected even it's a small drops of the water, and stopping action of the user is detected by the difference of the upper flow and the lower flow. So um, for people in experienced in musical theory, it's not very difficult. It's not very easy to understand the dynamic flow of the music. Also, analyzing music by focusing only our auditory attention is difficult because the flow constantly changes cannot be controlled. So we focus on the easy control, but not perfect control of the music flow using the water. No need to practice, just to play, and no need to learn music theory. So next, I'd like to move on to sweet body and mind that include my current work, that's past work, which is described by Kenji Matsuya. First, I'd like to talk about the living being and body. So we have 70% or 60% of water in our body, and including blood, sweat, and other things. And our body cannot be controlled if we have instinctive and strong emotions. So there are very strong body emotion connection. And also the water and fluid in our body are affected by such emotion. This is my student work using the sensor of heartbeat at the fingertip of the user. And here is a blood tank, blood tank to provide some water blood flow at the motion of the heartbeat, which is controlled by water tank and servo motors. And another one, can you see here the robot hands can have some sweat to express fear or strong emotion. And not only sweat, we use goosebumps to express its own instinctive emotion. And the robot hand moves flexibly, but it have not so soft body, but it have water. Okay, next I'd like to introduce you the breathing robot with lung. To be like living being, it makes some airflow, not water flow, but the user can feel some activity of the body, even its very artificial presence. And also, uh, the stuffer toy is very flexible, and we can imagine if it have some very soft meat flesh. So we adapted such robot. So our focus about the soft body and flexibility with music is based on the interest to living being, and also the flexible body have also controllable and uncontrollable presences factors. So the user can feel some softness and user can listen to the musical sound connected to emotion of the presence. The presence means the artificial being. This is also not presented in the proceedings. Okay, okay, sure. So there are some of stuffed toys work, but I'd like to conclude that the animals and humans have water in our body, not only interacting with water on the outside. Water is the most special fluid to make humans to keep uncertain feeling of the outside world and the own body. The tactile music interaction using water toys are expected to generate our fundamental and primitive bodily sense and emotion simultaneously. The fusion with the sound and fluid water also expected to create a novel experience for the user. Such experiment might generate strong emotion, we believe. Thank you very much. Sorry. Thank you very much.
So this is a good example in terms of interface technology, where you've got the water engages with the technology and the human engages with the water as well. So it kind of puts the water at the center in terms of interface taxonomy. So very, very interesting. Next, we've got Florian up to present on some water, kind of getting to understand the water, towards beginning to understand WaterHCI. And yeah, let's take it away, Florian. Can we hear you?
Your mute is on.
You might be asking for a little bit of time.
Yes, yeah. Hello. I think you should be able, hopefully, to hear me now. I was trying to share my screen, but my computer is a bit slow, so it didn't recognize the unmute click on it. But I think you should hear and see me now. Is that all correct? Just give me a thumbs up. Beautiful. All right, so I'm sharing the screen now, full screen, and swap the display. So you should see this now, full screen, and I'm ready to go. Can you just give me an okay that this is all working? Awesome. Good. All right. So my name is Floyd Müller from the Exertion Games Lab at Monash University in Melbourne, Australia. And I'm going to be talking today about towards beginning to understand WaterHCI. I realize you don't see my video. Is that correct? I had it set up. Give me 1 second. All right, let's try this again. Apologies. Beautiful. Thank you very much for that. All right. I'm working on it. It's just a bit slow trying to run that software together with that. Here you go. So again, my name is Floyd Müller from the Exertion Games Lab at Monash University in Melbourne, Australia. I'm talking about towards beginning to understand WaterHCI. A lot of people contributed to the work, so I thank all of them for their contributions. And I'm going to talk about mostly from a previous work that we've published under the title of 6 Degrees of Water Contact. There's a bit more in there, but most of the work, yes, as I said, is from our wonderful collaborators that I acknowledge here, please. I'll start with talking about, of course, why we are interested in WaterHCI, in particular playful WaterHCI, because we're very interested in playing with water. I'm going to talk about 6 degrees of water contact. So these are our this is our main contribution, and that allows us to identify 27 design features. I don't have time to go into all of them, so I'm just going to highlight a few of them, and they're important because they allow us to see an effect of a degree of the water contact on the design features. And then I conclude with some, I think, exciting opportunities for future work. So why are we interested in water? Because water invokes a lot of emotions in us. It can be fear, but also be excitement, serenity, and so forth. You all know about that. And water has been included in play throughout history. Here's a picture of a castle in Austria. I've been there myself and tried this out. So the idea was that the owner of the castle invited his guests to his estate and said, let's have a picnic out in his garden. And then they were seated on this table for the picnic, and he had a lever on the side that he could trigger, and then water would jet up from the seats. And of course, you know, like they would all jump up and laughter abound. However, when we look at digital water play, we find it's rather underexplored. This is a picture of what Red Bull did recently. They use brain-computer interfaces and eye tracking to figure out where surfers are looking at when they are surfing. And you can see that thanks to technological advances, we've now been able to do BCI eye tracking in water, not just waterproofing it, but also make it robust enough to physical water play. However, that study wasn't really an empirical study. It was more like a PR exercise. So we don't really have too much information about that. But we acknowledge that we can do digital water play is more approachable due to the advances in digital sensing technology. And we want to leverage that fact. So here the target audience are designers, researchers, practitioners, artists, both from academia and industry. And for that, we identified that we can categorize the amount of water contact when it comes to technology and categorize them in 6 different aspects or perspectives. I'm going to give you a brief overview of all 6, and then I go into detail after that. So this is about vicinity, because we argue that even if you're just sitting next to a pool or on the beach, just the reflection of the sun on the water, the temperature coming from the water already affects your experience. Sporadic contact is about rain and getting rained on or getting sporadically in contact with water. On top of water is about the aforementioned surfing or kayaking, paddling, and so forth. Partially submerged is the kind of water play that you often have or when children get in contact with water first when they play on the beach. Floating mostly refers to swimming, and underwater to diving. And there's HCI work that covers all these different degrees of water contact. For example, give you an example for each. The Steve Benford's lab in the UK did mixed reality performances, what they call, where they had a curtain of water coming down and then they projected onto that. That's for us an example of engaging with water from a vicinity perspective. Sporadic contact is an example. Here's Waterball Z or Waterball Z. It's an augmented fighting game using water as tactile feedback. On top of water, examples for that are coming out of the Swim Games project in the Netherlands, where they designed with children and teenagers games in which swimmers often jump in the water, and that is detected by a Kinect, because obviously the Kinect works better above water than underwater. So this is the top of water perspective, that our degree of water contact that I highlighted earlier. When it comes to partially submerged, we can point to some of our own work, thanks to Sarah Jane Pell, who developed these autonomous robots that are in water, and you interact with them by partially submerging your hand in order to play with these little robots. Floating refers mostly to water, as I said. An example of an HCI project that engaged with that is Moby Dick. It's an interactive multi-swimmer exertion game in which software detects the stroke that you are performing and then connects you with other swimmers in order to allow you to play a digital game together. Underwater is an example where people use augmented reality, but put people in the pool so they can actually swim in a real physical pool, but experience virtual fish and coral reef. And now that we have these 6 different degrees of how we can engage with water, we argue it might be useful to now look at the following 4 things and how they are affected by water when you bring the player or user and the computer in contact with water. So these are the state that the player or the computer is in, sensing, acting, and networking. What does that mean? Well, we argue you should look at both from a player perspective, what water affects the player across state, sensing, acting, and networking, but also in terms of the computer, how water affects its state, sensing, acting, and networking. And when we do that, we end up with all these different constellations that I mentioned earlier. But as I said, have time to go all of them, so I'm just going to highlight a few of them. So for example, if we look at the player and the contact with water, their state changes, right? So obviously, for example, if we look at breath, you have to come up and get some breath. So we need to consider that when we design. Similarly, we can look at the computer and the state of the computer. When the computer comes in contact with water, the state is particularly important. For example, battery life changes when a computer becomes in contact with water. Electrical insulation is another example, right? We need to electrically insulate the computer in order to make it work when in contact with water. Sensing, similarly, right? So we can talk about how, or we can consider how water affects the hearing of a player. But we also need to consider how the computer sensing is affected, for example, through vision sensors. We can't really use the same vision sensors that we use above water, or if we do, we need to consider different lenses and so forth. Same applies to acting, so that's the third aspect here. Our dexterity changes, our exertion changes when in contact with water. For example, we can't run as fast underwater than above water. And similarly, we have to consider how the computer changes, how we think about audio. For example, we can't really use the same speaker underwater, or at least the speakers still work underwater, but obviously some frequencies work better than others, the distance is different, and so forth. Last thing is networking, right? So this is how people communicate with one another. So our communication obviously changes underwater. We can't speak, for example, when we're diving. And our human proxemics changes, which is the distance that we have with other people. Our distance changes when we're in water with other people, for example. We always stay so far apart that we can do a stroke kind of actions to stay afloat. And similarly, if we look at the computer and the effect water has on the computer when it comes to networking, you can see that our wired connections changes, as well as our wireless proxemics, right? So wireless networks, if you put a Wi-Fi network underwater, then it still works, but not to the same extent that it does in air. So these different states allow us now to look at from the player and computer, look at the player and the computer perspective when coming in contact with water. And that allows us to create this table. So what I just showed you now is these, you put these on the y-axis, and what I talked about earlier, the different ways of how you get in contact, we can put it on the x-axis. That creates us this nice multi-dimensional table with all these different cells in it. And the extent of the water effect, we can now color in these different shades of blue, because we can see that when it comes to underwater, the player design features are affected to a higher extent than, for example, when you only consider the vicinity of the water. Again, I don't go into detail of all these cells here, but I just want to highlight that this kind of thinking helps us now to determine where are the challenges and where are the opportunities. And we can do that not only for the player perspective, right? How is the player affected by water, but also how the computer is affected by water, right? Obviously, when we look at the computer and the challenges when it comes to the technology, we can also highlight that with different colors of blue, high extent, low extent of the water effect. And just to sum up, I want to highlight that these different shades of blue allow us to see these challenges, but rather to see them as constraints. I want to highlight that we can also see them as opportunities. And I think a really nice example for that is Jelly Stomp, a game that actually uses these constraints but turn them into playful opportunities. The game works in the following way. It uses Sony PlayStation Move controllers that wirelessly via Bluetooth connect to the actual PlayStation. And the game designers, they programmed the Move controllers in a way that if the connection is alive, then the controller lights up. If the connection breaks, the light goes out. And your goal is to keep the light on. The game designers nicely waterproofed the controllers by putting them in condoms. So they made them waterproof, and then they attached them to the player's legs. And it's played in shallow water, like in these puddles or on the beach or in shallow rivers. And the goal is to constantly keep up the light, i.e. keep the Bluetooth connection alive. So what you have to do is you basically have to lift up your legs constantly and jump around in order to keep the Bluetooth connection alive, i.e. don't get the PlayStation controller underwater because it breaks the connection, therefore the light goes off. So it creates this interactive water dance as a result of seeing the constraint of limited wireless connectivity when it comes to water, turning that into an opportunity. So in conclusion, I present a lot of opportunities when it comes to digital water play for knowledge growth and innovation. We highlighted that there's a different effect of the water across different degrees of water contact. And we encourage you to see constraints of the water environment as opportunities. I want to highlight that our taxonomy of the 6 degrees of water contact is just the first step, and we really want to encourage you to design for these different cells that are highlighted, so we can begin to really grow the field of water HCI. And with that, I conclude my talk. I show you again the 6 degrees of water contact that are part of the talk of towards the beginning to understand water HCI. Again, I acknowledge all the people who are involved in that work. Again, my name is Floyd Müller from the Exertion Games Lab. Thank you very much.
Oh, okay. Excellent. Yeah, that was a very good talk. And I mean, one thing that's interesting too is the ordinality here. I was just saying, like, vicinity on the left on the slide, and then you've got sporadic contact. Like, if I look from, say, my own experience, like this morning I had a shower, which is sporadic contact, and then let's say you take a ferry. There's a ferry that takes people across to the island. To me, I would say a shower is more water. I feel wetter in the shower than I do when I take a ride on a ferry to the island. So I'm not sure the ordinality, like I like this taxonomy, but I'm not sure it makes sense to think of it as a taxonomy. I think of it more as an analog, like a continuum. You could say, well, how wet do I get? That's one dimension I could put. Or because the ordering could be permuted, and so we might not even agree whether a shower is less contact with water than a boat ride. But but I still think, it's interesting. And then I guess the other thing that we talked about too is whether the water goes in you or you go in it. So there's this idea of submersion, but then there's the other side when you put water in yourself. So you can either put yourself in the water or put the water in yourself. And so I think it would be fun to kind of play out some of these things. Like we could almost consider some sort of analog or continuous or undigital taxonomies that say the degree of wetness that you experience, which could be a continuous floating point number, how wet you're going to get on this ride, for example, versus other things like that. I think those would be fun little ways to carve up the space.
Yes, yeah, absolutely, totally agree. To your question about like water inside you, like when you drink water, we're doing a lot of work also on human food interactions, and that is not captured by the taxonomy, right? And we acknowledge that, and that's a limitation that where we really went like, okay, we only look at that things where you go into water rather than water into you. So yes, yeah, that's certainly a limitation for that. The dimension, yes, yeah, we really see that as a dimension and just use these categories to roughly identify key steps along the dimension. So we do see that rather as a dimension where you, like, as you described, it's more like a slider where you move along, because obviously, yeah, your example with a shower, right? So if I have a really high pressure shower, it's different than if I just have a few drops coming out of a broken shower. So we see that as a dimension where you move along or can move along. The designer can move the experience for users along. But I think it's still helpful to have these broad categories along it, because I would say that having a shower is, significantly different than actually diving into water. So that's where it kind of comes from, our approach of using categories along a dimension. But yeah, I totally agree that.
Yeah, that was. Is Atlas here? Is Atlas ready to speak at 6?
Just went down for a sec. Yep, he is.
Okay.
You can. Okay, keep going.
Oh yeah, so yeah, that's good. It's quite nice to see, we could build that out. We could sort of build on some of these ideas and create. One of the things I often think about is imperatives. Like when you go down to Ontario Place, they used to have no swimming signs there. And then there was a film production company came and wanted to do some filming on the beach, so they took the no swimming signs down. And fortunately, they left them down. There are so many of us swimming. By then, we had about 200 of us on many days. We'd have 200 people on the beach swimming during a no swimming day, like when there's a no swimming sign, and the security guards would come and tell us to get out of the water, and people would just stand the ground and stay in the water and say, okay, well, we're in federal land because it's a province up to the beach. When you cross the watermark, you're into national waters, federal land. And so in some sense, if they tell you not to swim, it's like unlawful confinement or where they're false imprisonment, where they're trying to keep you in the province and prevent you from going into the country, across the provincial border. And so we kind of got into all these discussions, but a lot of these imperatives come down to like no swimming, no fishing, no drinking of the water. And when I think of hard imperatives, I think of hard-edged taxonomies like the law and police and everything, like taxonomies that have very crisp, well-defined edges, but then there's taxonomies that have softer edges that are more human rather than legal. And so it's kind of interesting to look at some of these differences there and how we can carve up the space. And I'm sure in the days that come, we're going to keep the site alive and continue to take input and continue to create interaction and dialogue. So I think it's going to be a lot of fun. Next up, we have.
Yeah, actually, yeah.
Go ahead.
Oh, no, I totally agree. Like we need to bring fun in our interactions with water. I think that's one of the key opportunities when we design technology for water, that we can actually support and amplify playful interactions with our life in order to really help people to figure out who they are, who they want to become, and how to get there. And I think engaging with water in a playful manner is a key way to get there. And that's why I know you want to introduce the next speaker. That's why I'm really looking forward to that one, because I know they're kind of trying to do that with their really cool work that I really like.
Yeah, and I think that's really good. In terms of fun, I remember when I was up for tenure, on the road to tenure, my colleagues all told me, well, you should not be having fun. Don't have fun, and also don't appear to be having too much fun, because you need to be serious in order to get tenure. So then, in response to their advice, I called myself the Frolic Lab. So I said we kind of wrote a paper like first splashes at the Frolic Lab. So we kind of became known as the Frolic Lab, fun and frolic in this lab. And then I started holding for a while I was giving my lectures in the fountain. At Stanford University, there's a fountain out in front of the university, right out in the main entrance. And I decided for almost a whole year, I didn't wear clothes. I just had my bathing suit on, and I would just come in and go to the fountain, and I held all of my lectures in the fountain. And I had all my meetings in the fountain. If somebody wanted to meet with me, I'd schedule it in the fountain. So it was kind of fun. I think I ignored the advice of the people who were saying not to have fun. But
and
anyway,
you got tenure. See, that's what I mean.
Yeah,
like,
I
life's
somehow,
too short to not have fun.
But I had to publish about 10 times as many papers as the minimum requirement normally would be, because you've got a higher hill to climb when you're having fun, because people don't like to see you having fun. They want you to be serious. But anyway, on that happy note, I think we'll bring Atlas in here, because I'm just loving to see what's going on here. And it'd be super fun to connect with Atlas. It'd be awesome to connect with you in some way in the future. And so take it away.
Thanks a lot for that introduction, Steve. We definitely do like to have fun. Let me share my slides here. So it has not shared my slides yet, is that correct? What? Okay, now I think it's working. Beautiful. Okay. Hi, everyone. Thank you for joining my talk on storytelling in water with aquatic virtual reality. My name is Atlas, and I'm the Chief Content Officer of Ballast Technologies. Using our proprietary virtual reality headsets, we provide memorable experiences to guests while they are submerged in water. The feeling of floating in water, combined with the visuals, combined with the sound, all complement each other to create an impression that is much greater than the sum of its parts, and in many cases can be quite profound. In this talk, I want to share with you how we got to where we are today and what it's like to tell stories in water. There are really two different modes of stories that we tell in water. One is on water slides, one is while snorkeling, and one is while floating. They are all very different, and I think they are all quite interesting. So in August of 2017, my two co-founders and I were invited by one of the world's largest water parks in Europe to move to Germany and develop the first virtual reality on a water slide. Our assignment was to take an existing water slide, just a traditional water slide, a steel tube, no technology on it, and turn that into a virtual reality attraction. That means people would sit at the top of the slide on a raft as they did before, but they would put on a VR headset, get pushed down the slide, and then as they bobbed and weaved down the slide physically, they would have this experience of flying through various fantastic landscapes and seeing various things. This was a really important project for them because water slides are these large, expensive, immobile structures. And once they're built, it's really impossible to change them in any meaningful way. If your park visitors get tired of the basic slide experience to any extent, the only option is really to rip it out and build a new one. So if we were successful, the feeling of a water slide could be changed over and over through the magic of software, which would be really transformative for the industry. This is a very technical group of speakers, so you all know what virtual reality is and how it works, but for the audience, there are really three pillars to making VR work. One is the headset that you wear on your head, and what is special about that headset compared to watching television is that it blocks out everything about the world around you so that you just see the fabricated virtual world and your brain can start to believe that it's there. The second aspect is the tracking system, because when you're in virtual reality, if you move your head to the right, for example, the virtual world has to move to the left by the same amount. And that's what gives you this illusion. That's what creates the magic of being able to poke your head about and move and look and really feel like you're part of a world that's real. The tracking system measures what your body is doing and changes the visuals accordingly. And finally is the content, what you see and experience during your virtual journey. So our challenge was to basically reinvent these core concepts of virtual reality for this water slide, in addition to come up with operational solutions required by a high throughput ride. That meant creating a waterproof headset that could be used by the park. It meant inventing a custom tracking solution, which could deal with the high speeds and chaos and wetness of a water slide. And it meant coming up with content, because the content had to be customized for each slide, since the shape of the journey you might take really has to match the physical twists and turns that you take on the slide. And then operational solutions were needed, like the ability to charge headsets while wet and sanitization solutions and so forth. It took us about 5 months to complete this first project and invent all these things, and it turned into a success. The park was thrilled with what we gave them. Ever since then, they've been running about 10,000 paid rides per month at this one location. And for the months that they've been open, that's total to nearly 400,000 paid rides to date at this location. And thanks in large part to the success of this first installation, we had the opportunity to do a half dozen installations all over the world on different water slides. One of the great things about this system is that we let our guests select what experience they're going to have on a water slide just before they go down it. And they could go down it multiple times if they wanted, and to have a different experience every time. From a storytelling perspective, there are all these experiences share some constraints. They all have to be brief, really just the length of the water slide, which is about 30 seconds. And they all have to have non-stop motion involved, because your body doesn't stop throughout this experience. So the experience has to reflect that motion. These were all very challenging and interesting constraints from a storytelling perspective. So I'd like to share with you how we solved them for one particular VR slide experience. This is one of my favorites, and it takes place in a fantasy-themed experience in a snowy landscape. When the guest first puts on the VR headset, no one knows how long they are going to sit at the top of the slide. And this is because it is up to the ride operator, for safety reasons, to decide when they will push the rider to begin their descent. This is just a still image, of course, but while they are sitting at the top of the slide in an animated fashion, the initial scene really sets the tone of what they're about to experience. So in this case, they would see falling snow. They would see a dragon ominously flapping its wings over a castle. They would see smoke and fire, and they could look around and really start to sink in and believe where they are, and start to understand that there is danger and a battle happening here, and start to absorb the realities of this world. When the ride starts, the participant moves rapidly through the virtual world and the action starts. In this particular case, the dragon swoops up over the walls and then hides just out of view behind some trees. The guest goes around the trees and discovers there is a charging army of medieval humans. And around the next bend, they find themselves in an epic clash between this charging army and this fire-breathing dragon. The dragon notices your presence and decides to ignite the bridge in front of you, and you escape just in the nick of time through this opening in the rock wall, where you discover deep under the mountain a magical cavern. And eventually you come to rest at this dragon's nest that has 3 eggs and a baby dragon inside of it. And that's how the story concludes, creating this implication that the terrible dragon is actually just protecting her brood and her babies because her nest is nearby. And this is one example in how just 30 seconds and in this constraint of a fast-moving experience, we set the stage, tell the story, and bring it to an end in an efficient manner. So our VR slide system was a great success, but after creating that, we really wanted to come up with different kinds of experiences, stuff that would lead to really deeper immersion and longer experiences that could lead to more intimate connection with the subject matter. So after VR Slide, we immediately hunkered down and created Diver, which is a system that would bring VR to the swimming pool. In Diver, participants put on a waterproof virtual reality headset like before, but this time, instead of sitting on an inner tube, they wear a flotation band, they lie face down in water, and they breathe through a snorkel. The flotation band is tethered to a weight at the bottom of the pool with this elastic band, and this gives the participant the freedom to move their body in a natural way. They can swim if they want to, they can twist, they can turn, they can explore, but really they are held in place physically, so they're not going to crash into anything. They stay in their own little safety bubble. And from a safety perspective, it's worth noting that this is only done in shallow water, and there's always enough slack on the line. They can instantly stand up without any impedance if they decide to end the experience and go above the water. This model of holding people in place in the water as they explore this virtual worlds turned out to be incredibly effective. On land, you have this strong sense of whether you're moving or not. For example, if I put you in a chair and gave you a virtual reality headset, the illusion wouldn't be complete. If the VR was moving, you would know that you weren't moving, unless I went to a lot of effort to pick up your chair, shake it, move it around, create accelerative forces for you. Your brain wouldn't be fooled. But in water, that is very different. If you think about if you're caught in a current in the ocean, for example, if you close your eyes, you really can't tell if you're being dragged rapidly to the east or rapidly to the left. The nature of water makes it so that the participant's mind really accepts whatever virtual perceived motion it is presented with. So with that said, here is an example of one of the virtual reality experiences we offer for the Diver system. Because of the relaxed feeling and pace of floating in water, Diver experiences really lend themselves to slowing down and taking in the sights. So in this particular experience, there's a lot of oceanic animal life that swims around you and you get to explore it. There are a lot of beautiful coral reefs, there are caves, there are sun shafts, there's a lot of plankton that dances in the light as it catches the light. And for this story, this particular experience, the story we tell is one of a baby whale that is caught in fishing lines surrounded by sharks that are circling around it at the beginning of the experience. That sets up the tension. The baby whale escapes from the lines and the sharks, and you get to follow it for the next 5 minutes as it searches for its family. and you go past shipwrecks and coral reefs, and you go through kelp forests. And at the end of the experience, the sharks catch up with a baby whale, and there's a rescue where the whale's family comes in at the last moment and chases the sharks away, and the baby whale is reunited with her family. Even though our diver system takes place in the water physically, it really works with any subject matter where either flying or floating or falling makes sense. So for example, in addition to our water-based experiences, we let people explore the International Space Station, and that works just as well. We also have an experience where people can go skydiving and flying in a wingsuit and look around and see their squad flying with them, and that also works quite well. In 2020, we were invited to the Sundance Film Festival, where we presented a 9-minute experience in a pool there. We ran 3 stations in the pool of Sundance headquarters. We partnered with a filmmaker, Pierre Fouquet, who made this particular film. But it was really interesting to see the traditional film setting and how well aquatic virtual reality worked in that setting. Since inventing Diver or creating Diver, it has launched in dozens of locations. Here are some of the most significant ones. And after our successful Diver launch, we teamed up with a talented aquatic attractions company called Subsea Systems, and we created Diver Plus. And Diver Plus is a haptic feedback unit that takes the form of a stationary vehicle that gets mounted to the side of the pool. This is an add-on to Diver. You can see how the participant is wearing our standard Diver system on his head, but now he is also holding this haptic feedback unit. The unit can propel water towards the participant at various speeds. These changes in speed are timed with the experience, and this can create the feeling of acceleration and deceleration as the story requires it. It can also blow air bubbles out of that front opening from compressed air canisters at key moments, and having the air blow past your body creates sensations such as brushing past seaweed or brushing through schools of fish. Or if you're flying, it might give you the impression of having a near miss with some rocks because you have the slight sensation on your body. And it can also shake the handles, which gives you this impression that you're holding this very powerful vehicle that's accelerating. Within the experiences themselves, we show virtual arms and hands of the participant holding some kind of virtual version of this vehicle. So for example, we'll show you holding a high-speed underwater scooter if you're exploring the ocean, or holding some kind of jetpack vehicle if you're exploring outer space, or maybe holding onto a hang glider if you're flying over landscapes. And because of the large amount of water that we can make rush past you from this unit, it can achieve some of the highest perceived virtual motion of any of our systems, which can give you this really thrilling feeling of having traveled literally miles within a 5-minute experience. We've also experimented with virtual reality in float tanks. This was a very interesting experiment for us. We wanted to see what it was like to create even slower, more long-form meditative experiences. So we created a 17-minute experience called Breathe. In this experience, the participant is invited to breathe in time with various jellyfish that they encounter. These are friendly jellyfish. They're very ethereal. They're glowing. There's all these sparkling lights going down their inner structure. And everything in the experience pulsates brighter and darker and open and closed with the undulating rhythm of a slow human breath. Even the water around the participant swirls and gets brighter and darker as if the water is filled with millions of pieces of bioluminescent life that are all breathing in unison. As the experience progresses, participants get to encounter different species of jellyfish. This one has these long, beautiful skirts, and the head of the jellyfish expands during the human in-breath. And then as the participant exhales, that glowing light travels through the skirts, almost as if the jellyfish is squeezing out the breath, and it really enhances this feeling that you're breathing with this glowing, beautiful, ethereal animal. One thing you really can't express in a presentation is just how powerful many of these experiences are when you're really doing them in water and in the actual system. But if you're passing through New York and would like to try this experience, Next Level Floats in Brooklyn is providing Breathe as an option for their floats. Thank you for joining me on this recap of our journey, exploring this strange and exciting new storytelling medium of aquatic virtual reality, from fast-paced VR slides on one end of the spectrum all the way to these slow meditative floats way on the other end of the spectrum. I hope this talk has given a glimpse of how magical and transporting storytelling in water can really be. It's been a really thrilling journey over the past 4.5 years, discovering all that this medium has to offer, and I'm excited to see where it takes us next. If you'd like to learn more about the work we do at Ballast, including some videos of our installations in action, you can visit us at ballastvr.com, or I can be reached at atlas@ballastvr.com. Thank you very much.
Thank you. That was absolutely wonderful. That was really, really good. Very, very, very nice to see, and we'll definitely continue to be in touch through the website and everything. And so we'll stay in touch. We're gonna have lots of fun together, and so we'll get the proceedings out by the end of the day. If anybody has any thoughts on that, on what's in the proceedings so far, and hopefully we'll get that out, and then get digital object identifier for it and everything, and then we're going to continue working on it. We got that Cyborgs conference coming up in a little bit later in another few days, and that might be another chance to get a redraft or a remix of it and kind of take more input. So if anybody has input immediately for the proceedings that are going out tonight, or if anyone wants to join us and join in on the next phase of this development for the deadline in a few days, that'll be wonderful to hear from. And I want to keep working together on this and keep the discussion going. I think there's a good opportunity here to kind of bring people together and celebrate. We continue to celebrate Ontario as and Atlas, we should get you up here to Ontario, because we're doing a lot of really exciting things with water here, and it would be super great to talk about what we can do in the Canadian sector, as well as in, I've got a place in Palo Alto and a place in Toronto as well, so I'm back and forth, so maybe we'll see what happens in the nexus between California and Canada, Ontario.
Great, sounds good.
And yeah, I hope we stay in touch and continue having some fun. And yeah, thank you everybody for participating in the 23rd annual WaterHCI DECONference. And we've done many fun things over the last 23 years in this sort of vastly growing field. And I hope that we continue. Maybe DECONference 2022 hopefully will be held. I don't know. Maybe, who knows what'll happen. It's traditionally we've always held it here in Toronto because it's just been kind of a small thing among a few friends and everything. But as it grows, maybe we'll talk about moving it to California, or moving it to a water slide, or moving it to a water park. I'd love to host DECONference 2022 in a water park with VR water slides and all this kind of fun stuff too. Who knows? Anyway, I'm open to ideas. Let's keep the discussion going and have some fun and frolic. And it's been fun. Everybody told me I should be a ladder climber and I should do the right thing and be serious and do work and try and advance my career and everything. And instead just decided to have lots of fun, and I think I don't regret any minute of it. So stay in touch and keep let's keep it going. So thank you, and we'll post all kinds of stuff. We had a really great swim today. We'll post some materials. We'll post the talks on the proceedings, so we'll put the conference proceedings on the website, and we'll also put the videos up. If any of you have slides you want to send me, or if you've got self-recorded videos, if your recording turned out better than we recorded all the talks here over the web, but there's a bit of delay. So if any of you recorded the talks yourself or have slides, send us that material so we can put that together with the proceedings. And it's been fantastic. Thank you.
Thank you.
And thank you for all the people that helped, Ryan, Caden, and Dr. Draw, and Perry, and everybody else at SwimUp, our 560 members of SwimUp, and thank you to the McLuhan program and all the people in the Equivalence Working Group, and thank you to everybody at U of T who's helped over the last 23 years, and all the people who've been involved in this project. Thanks so much for all your contributions and help. We really appreciate it. It's wonderful to have all these smart people joining us, all these smart and fun people joining us. Good.